Hi, I'm Jingwang Ling, and I'm glad to present our paper, Semantically Disentangled Variational Autoencoder for Modeling 3D Facial Details. This research is performed by me and colleagues from Tsinghua University, Intel Labs, and SenseTime Research. We have seen the broad applications of 3D face reconstruction in augmented and virtual reality, especially in the era of the metaverse. These face reconstruction methods typically fit a face model to a video of a user's performance. They can reconstruct accurate large-scale shapes represented by a few, typically hundreds of, model parameters. However, the reconstructed faces are over-smooth and do not quite resemble the user because they lack realistic wrinkle details. To address this, some works go beyond the representation space of a face model to reconstruct facial details. The problem is that they need to store the details as high-resolution meshes for each frame, posing a challenge to the bandwidth if we want to stream the facial performance over the network. In addition, these details cannot be driven by facial animation to generate novel expressions. Let's look at current face models to dive deeper into why this happens. Most face models are linear morphable models that decompose the possible facial deformation into hundreds of identity and expression bases, and they can independently control identity and expression. However, it is commonly observed that linear combination of these bases cannot generate sufficient facial details. There are also attempts to learn facial representations from the 3D mesh dataset using neural networks, but we have not seen a representation incorporating facial details. In addition, while they can separate identity and expression into different sets of latent codes, the latent codes do not have explicit semantic meaning. That is, we don't know which code controls a mouth open or a laugh. Motivated by this, we set our goal to build a morphable detail model to compactly represent facial details. With a model at hand, we should reconstruct the details using data-driven priors in the model. After obtaining the reconstruction, the user should be able to animate the face using knobs or sliders corresponding to specific semantics. We disentangle expression and age from facial identities, as they are two main factors that affect facial details. Our research answers the following questions. First, is it possible to model facial details? We use experiments to show that details, high frequency and high dimensional as they are able to be modeled. We are inspired by biological perspective that facial details are caused by shared anatomic structures of facial skin, soft tissues, and muscles. And to model facial details, we find that using a variational autoencoder achieves better representation than commonly used linear models. First, we represent 3D facial details as a displacement map, where each pixel encodes the displacement along the surface's normal direction. To generate a high-fidelity face, we first generate a smooth face using a morphable model, and add the displacement map generated by our detail model. To learn the facial detail distribution of human faces from a population, we train our detail model on the Facescape dataset, which contains more than 800 people with 20 expressions each. We also obtain expression and age information for each sample in the dataset, which are blend shape weights and age values recorded during capture. First, we train a variational autoencoder of displacement map using reconstruction loss and KL divergence. To control the expression and age of the generated details, we condition expression blend shape weights and age values to the decoder. We have the dataset's expression and age information for each training sample, and during testing, we can fit the input's expression and age and manipulate them to generate novel details. To independently control identity, expression, and age, we need the latent code to only contain information of specified semantic labels. That is, they should be disentangled. We use adversarial training to achieve disentanglement by training two discriminators to tell coupled distributions from independent distributed latent codes. To provide training data for the discriminators, we permute latent codes within mini batch to generate samples from the hypothetical independent distribution. It can be viewed as minimizing the divergence between the joint distribution and the product of marginal distributions. When using the model, we can fix decoder weights and optimize the latent codes to fit the input constraints. After obtaining the latent codes of test input, a user can manipulate these semantically meaningful latent codes to generate detailed facial animation. We can fix the decoder weights and fit the latent codes to a facial scan, thereby embedding the scan into a compact 300-dimensional latent space. We can faithfully reconstruct the scan and append the missing parts using model priors. Our model can reconstruct a detailed 3D face from a single image. The reconstruction method is essentially shape-from shading, but with the Laplacian smoothness replaced by our data-driven regularization. Our method both accurately reconstructs wrinkle details and is robust to shadows and occluding hair. Our model uses blend shape coefficients. Therefore, users can use their performance to drive the face to generate detailed animation. And our model can generate dynamic details corresponding to the driver's expression. By varying the age coefficients from young to old, we can produce aging effects under different identities and expressions. Both the original face and the aged one can be driven to produce animations, and these show different dynamic details because of the changed age. Finally, we also show tracking results of a user's performance using our model. The method is similar to image fitting, and we add a temporal term to achieve temporally stable reconstruction. Since each frame can be represented by hundreds of latent codes, it requires low bandwidth to stream our tracked performance. To conclude, we propose the first semantically disentangled morphable detail model, which allows accurate reconstruction and semantic-specific manipulation of facial details. We effectively disentangle the latent vectors of identity, expression, and age under the framework of variational autoencoder in an adversarial manner. Future work can improve the expressiveness of the detail model on pore-level details and details that are rarely seen in the training dataset. Thanks for your attention.
Hey everybody. So welcome to the modeling session. I'm A.B. Campbell. I'm going to be your session chair. So we're going to open it up to Q&A now. Anybody have any questions? Center. You have a roving mic? No? Oh, yep.
Hi, thank you for your presentation. Could you please explain a bit more on the disentangling on the latent vectors? Like what was the purpose of that adversarial training that you used? I think I didn't quite understand. Thank you.
Oh, okay. Thank you for your question. Yes, that's a very important question. And so we are representing the facial details, the detail face using a deep generative model, a variational autoencoder. So when using its decoder, it can generate a detail face from a latent code. A latent code is is like a feature vector of one layer of the neural network. And so if we don't do any disentanglement, it will mix all the information in those latent vectors. So we don't know which code in the latent vector controls identity, expression, or age. So we need to separate its information. I mean, so all the information before the disentanglement already exists in the latent vector, including identity, expression, and age. But we need to explicitly separate them. And so we use adversarial training on these latent vectors. We use two discriminators that input the latent vectors and tell if they are coupled or disentangled to divide the latent vector into three parts. Each part only controls identity, expression, or age. So did I answer your question?
Yep. Well, thank you very much for your presentation, and we're going to move on to our next presenter. So thank you, presenter. So again, we're going to have another online presentation. So Xiao Yi should be on there.
We present our ISMAR 2022 journal work, COLI BA, Compact Linearization-Based Solver for Bundle Adjustment. Augmented reality requires real-time motion tracking of mobile devices, and also needs a large number of virtual 3D assets. The former is realized by simultaneous localization and mapping, SLAM. The latter can be generated at a low cost by structure from motion, SFM. Bundle adjustment is the optimization module of both SLAM and SFM, and also the key to real-time and accuracy of AR applications. BA is a nonlinear optimization problem, which aims to optimize camera poses and 3D points by minimizing the reprojection error. From the geometric perspective, each reprojection error can be regarded as the Euclidean distance between the observation of 2D feature points and the projection of 3D points. In the past decade, researchers have done a lot of exploration on the sparsity and incremental manner of the BA problem. However, the clear geometric meaning of reprojection error still leaves room to improve the optimization efficiency. Besides, for large-scale BA problems, there are serious cache misses caused by large sparse matrix multiplication, reducing the optimization speed. To solve the BA problem efficiently without loss of accuracy, we propose COLI BA, a compact linearization-based solver for bundle adjustment. By reviewing the numerical calculation process in the BA solution, we found, in the construction of the Hessian matrix, the relevant part of each reprojection error can be represented by a 3D vector. This compact representation greatly improves the optimization speed and memory access efficiency. To further improve the efficiency of memory access, we propose a reordering strategy, which makes the structure of the Hessian matrix more compact and regular by adjusting the order of parameters. Thanks to the geometric properties, many calculations can be formulated with more compact representations. For example, compared with the redundant matrix form, Lie algebra can well simplify the derivation of rotation. To obtain better geometric form, we use spherical reprojection error instead of traditional reprojection error in BA optimization. This figure shows the calculation process of the reprojection error. Aij is a vector from the camera center Ti to a 3D point Pj. The traditional reprojection error measures the distance between the projection of a 3D point and the 2D observation on the normalized plane. And the spherical reprojection error measures the distance on the unit sphere. The benefits are that the Jacobian of the spherical reprojection error can be completely represented by three types of matrices: rotation matrix, antisymmetric matrix, projection matrix. These matrices only need a 6-dimensional vector to represent. The first 3 dimensions correspond to rotation, and the other 3 dimensions correspond to Aij, the vector from the camera to the 3D point. Besides, these matrices have significant geometric properties and can simplify the subsequent calculation. First, a block of Hessian matrix is equal to the corresponding Jacobian multiplied by its transposition. The rotation matrix can be eliminated in this process. After elimination, we can find that for a reprojection error, using only a 3D vector can construct its corresponding Hessian matrix element. We call this 3D vector the compact vector. Secondly, by observing the exponential operation of the antisymmetric matrix, we can find that there is a cyclic group with the antisymmetric matrix as the generator, and the projection matrix is also in this cyclic group. This cyclic group can greatly simplify the multiplication between the antisymmetric matrix and the projection matrix. With the cyclic group, the Hessian matrix has a very simple form, which can be directly calculated from compact vectors. Then, I will introduce the reordering strategy. The calculation of the Schur complement will involve the multiplication of 2 large sparse matrices. And the sparse block matrix corresponds to the upper right part of the Hessian matrix. In this sparse block matrix, each row corresponds to a camera, each column corresponds to a 3D point, and each non-zero block corresponds to a reprojection error. In the construction of the Schur complement, the calculation of each block matrix will involve 2 rows of the sparse matrix. These 2 rows correspond to 2 cameras respectively, and the calculation is only related to the covisible points of these 2 cameras. In most cases, the non-zero elements corresponding to covisible points are scattered in the sparse matrix, resulting in a large number of cache misses. Therefore, our core idea is to adjust the permutation of cameras and 3D points to make these covisible points arrange compact. We use a graph to represent the matrix structure. Each node represents a row structure, and the distance of each edge represents the similarity of the 2 row structures. In this way, the optimal permutation problem can be solved by finding the shortest path through all nodes on this graph. This problem is a variation of the traveling salesman problem. We use a simple heuristic algorithm to solve the problem, where we take the nearest neighbor of each node as the next node. The right figure shows the results of the reordering strategy on real data. We visualize the structure of the sparse matrix, using blue pixels to represent non-zero blocks. The structure of the sparse matrix becomes compact and regular after reordering. We compare the proposed optimizer with G2O and series on various datasets. In all sequences, COLI-BA is superior to the existing methods in memory consumption and optimization efficiency. The optimization speed of COLI-BA is 5 times that of series and twice that of G2O. We quantitatively measure the number of caching misses of different methods in optimization using the performance analysis tool. As shown in the figure, the proposed method has a good memory access efficiency which is significantly superior to series and G2O. In order to further prove the robustness and efficiency of the proposed solver, we also carry out experiments in real SLAM and SFM systems. We replace the optimizers of OrbSLAM and ColMap with the proposed solver. Except for the replacement of the optimizer, other modules and parameters are completely consistent. With the proposed method, the local BA of OrbSLAM only costs half optimization time. With the proposed method, the reconstruction efficiency of ColMap has been improved by 5 to 10 times. Using the proposed optimizer, we make a simple AR demo. We obtain the camera trajectory by COLI-BA-based SLAM. and reconstruct the virtual object by Coley BA-based SFM. With the camera trajectory, we put the virtual object into the scene images. Besides, we rendered a virtual laptop on the desk in the scene. Thanks for watching.
Thank you. That was a very interesting presentation. A lot of things we forget. That we've done a lot of innovation over the decades that I've been coming to ISMAR, but these speed-ups really matter and really allow new applications in the future. So, well, let's open the floor to questions. Yep, get a mic down the back there.
Hey, thanks for the presentation. So I didn't quite get whether this new speed up, like how much it changes the average trajectory error, like the displacement error and the rotation error. So do you have some comment on how it changed with the new system?
I might, just in case you didn't hear that. Oh, yeah, do you want to answer that? Or
the proposed method speed up the bundle adjustment without loss of accuracy. If you use the same cost function, the result is the same. So the trajectory, the accuracy of trajectory is good, and you can read our paper to see the experimental results about the camera trajectory.
Cool. Yeah, that answers my question. Thanks.
is there any more questions? Yep. More there.
I have a question about when you project 2 points on the image to the spherical sphere, to a sphere, unique sphere, why don't, I mean, in my understanding, this distance in the image plane when you project to the sphere, unique sphere, it must be the length of the arc, like the length in the sphere from the point to another point on the sphere. Why you use the Euclidean distance, but not the arc length?
Can you repeat the question?
It's like is in your presentation, in your work, you use the Euclidean distance from 2 points in the sphere, right? I mean, I want to
yes.
I want to ask why the I mean, what's about the length in the sphere about 2 points of 2 points?
Okay, I understand. The benefits of spherical projection arrow is that its Jacobian can be completely computed by 3 types of matrices, and they can speed up the construction of Hessian matrix. So we use spherical reprojection.
Yeah. Okay. Thank you.
Perfect. I think unless there's no more questions, we'll move to the next speaker. I believe the next speaker will be online and a video as well. So let's say, it's our current speaker.
Hello, everyone. My name is Wenlei Liu, and the topic of my paper is MFFPR, Point Cloud and Image Multimodal Feature Fusion for Place Recognition. Place recognition technology can eliminate cumulative errors and thus plays a vital role in SLAM. In this paper, the composite feature of point cloud and image data is obtained by multimodal feature fusion, thereby improving positioning accuracy. The place recognition methods of data-level fusion and feature-level fusion based on point cloud and image are compared. This paper verifies the proposed method on Semantic Kitty and New Scenes datasets. SLAM is also the core technology of AR/VR, which provides high-precision positioning information to obtain more realistic reconstruction scenes. We first integrate point cloud semantic features, instance features, topological features, and image texture features to obtain comprehensive features from different modalities. We design a data-level fusion and feature-level fusion relocation framework based on point cloud and image data, and compare the methods of data-level fusion and feature-level fusion. When acquiring topological features, we fuse the intraclass GCN features and the interinstance GCN features. Related work. Image-based place recognition, VLAD, NetVLAD. Place recognition based on point cloud data, LPNet, SGPR, EPCNet. Fusion-based place recognition, DP2P, MinkLock++. This paper designs two recognition methods based on point cloud and image multimodal feature fusion, a data-level fusion recognition method based on point cloud and image, and a feature-level fusion recognition method. Data-level fusion place recognition method. First, it is necessary to obtain the fusion data of the point cloud and image. Second, the semantic features and labels are obtained through the UNet. And the semantic labels are segmented by the CMeans++ method to obtain different instances in the scene. Then, use the instance segmentation result to construct an instance matrix and obtain instance features through PointNet. Use the GCN model of the same intraclass features and interinstance features for training, and obtain topological features through the MLP network. Finally, the semantic features, instance features, and topological features are fused. And then the final similarity score is obtained through the feature fusion network and the SIMON. Feature-level fusion place recognition method. Firstly, the point cloud data is obtained and outputs the semantic features of the point cloud through the UNet. Then, the semantic labels of each point cloud are obtained through the softmax layer. And the instance labels are obtained by the CMeans++ method. For image feature extraction, first, we obtain the feature information of the whole scene through ResNet 50, then, the image feature is extracted through the MLP network. Finally, the point cloud semantic features and image features at the feature level are fused. Point cloud and image data fusion. In the data-level fusion method of point cloud and image, the image color information is added to the corresponding point cloud data to construct color point cloud data. The image and point cloud data can be fused through coordinate transformation. Topological features. The relationship between nodes in each cluster represents the attribute relationship between objects of the same class. This graph feature represents the attribute feature of objects in the scene, which is only related to the object itself and has nothing to do with others. Using KNN to construct a graph model is to make the graph model include both similar and different objects. In this way, the construction of the model can make the information between different instances transfer to each other, spread their nodes' information throughout the graph model, and fully capitalize on the propagation nature of the graph model. Feature Fusion Network. The CNN model is used to extract and reduce the dimensionality of fusion features and obtain higher-level abstract features. The idea of the residual model is, first, Use KNN to calculate the cross distance between feature vectors instead of spatial distance, and select the nearest K feature vectors to represent the fused features. The residual vector can be obtained by making the difference between the KNN feature and the original feature vector, and then concatenating the residual vector and the original vector according to the feature dimension. Finally, the attention mechanism is used to strengthen the learning of important information and obtain the iconic residual feature. Experimental setup datasets. This paper mainly uses the semantic kitty and new scenes datasets to conduct experiments to verify the proposed method and compare it with the state-of-the-art methods. Evaluation method. The recognition problem is transformed into binary classification problems, and its loss function is the cross-entropy loss. Generally, the precision recall (PR) curve measures the experimental results of the binary classification problem. Quantitative comparison experiment. From the comparison results of the PR curve and F1 maximum scores, it can be seen that the methods based on data level and feature level fusion have achieved better results on the semantic kitty and new scenes datasets, with higher accuracy and more stable results. The recognition method based on feature level fusion is better than that of data level fusion. The main reason is that in the method based on data level fusion, some interference data are mixed in fusing point cloud and image data, which affects the effectiveness of the final feature extraction. The original data are first used to extract abstract features in feature level fusion. This process filters out the interferences in the original data and then fuses the extracted features to achieve better results and acquire strong robustness. Qualitative comparative analysis. A schematic diagram of place recognition of the Kitty 08 datasets, where the line segment intersected by yellow and blue is the recognition part. The dotted circle in the figure is a crossroad, and the two frames of place recognition are 2516 and 3862. In this paper, point cloud and image data are fused. The car in the dotted box in the figure is a common object that appears in place recognition. The points of recognition failure are usually different points on the same road section. The main reasons are that many scenes are relatively similar in the same road section, which makes it easy to cause overfitting through a single feature, and the ability to distinguish similar scenes is poor. The topological feature enhances the distinguishing degree of the structure, and the image feature increases the texture feature. Combining features can effectively improve recognition accuracy. This experiment qualitatively demonstrates the effectiveness of the proposed method. Robustness experiment. Considering the occlusion problem of dynamic on static marker objects, part of the point cloud data is randomly deleted and the image data is randomly cropped. We flip the point cloud and image data at any angle. Gaussian noise is added to the original point cloud and image data to simulate the sensor's influence on the experimental data. The fusion features include the underlying texture features and the higher abstract semantic and GCN structure features. Therefore, it can filter out the influence of underlying data disturbance on the results and attain strong robustness. Ablation experiment. This paper studies the effects of semantic features, topological features, image features, and their fused features on recognition, respectively. The fusion method improves the matching accuracy while making the result more stable, reducing the data fluctuation, and achieving strong robustness. Specifically, point cloud semantic features can identify and locate different types of objects. Topological features have better scene structure information, and image features have better texture information and supplement other features. Although the fusion method increases the number of parameters and calculation time, the increase is relatively small and falls within a reasonable range. Conclusion. In this paper, we proposed a place recognition method based on point cloud and image multimodal feature fusion and compared data level fusion and feature level fusion methods. The fused data from different sensors obtain the composite features of a scene. By fusing the semantic features, instance features, GCN features, and image texture features, our proposed method can obtain more comprehensive features and enhance the ability to express autonomous driving scenes. The GCN features merge the interclass GCN features with the interinstance GCN features. The proposed method achieved the best results on the Semantic Kitty and New Scenes datasets.
Now I'd like to open to the floor for questions. Anybody have any questions they'd like to ask our presenter? I have one. Just looking at the results of sort of the competing algorithms there, again, these data sets were mostly for car vehicles and driving. They were driving examples, I believe. Even with the down to 10 milliseconds, it seemed to be in sort of response time. Do you think that this is at a stage now where these sort of algorithms really should make people trust kind of driverless cars to use these sort of technologies? So, very open question, but it's what I always sort of see when these examples are given.
Pardon, your question, I don't understand.
So the example that you gave, the data sets you were using were mostly driving examples. So they were on streets and roads. So again, I'll phrase it a different way. So given that your algorithm and some of your competitors are only within sort of 1%, is there much more research to do in this field, or are we at a point now where we can really present this sort of accuracy that a driverless car would be able to detect where it is, its placement, and is there much more to go, or is it more now we should be looking at the trust and try to build up people's trust in them?
In this paper, we studied the police recognition technology. We use this method can calculate we use this technology can prove the accuracy of the police recognition. Some the accident and the person, I don't think this used in this situation. I see the situation the background is we transfer the town and the garden. We can use this technology in SLAM and can prove the accuracy.
So I mean, yeah. So there is more improvement, you think, to these sort of algorithms at this stage? More improvement possible, or are we getting to a stage where there's no more improvement really on these sort of data sets?
Yes, 就是I have some improved the accuracy and the background and didn't improve.
So we've improved the accuracy, but it's that flip side of if the recognition time is getting smaller and smaller, like is that the next improvement? Is trying to reduce, so if we're at 10 milliseconds, is that the next area of research? Because if recognition is at 0.999%, it's a huge recognition. The accuracy is really, really good. Is there not sort of space then, is the research should be in making this quicker and quicker in terms of the next stage of research following on from your work and others?
in this paper, we meaning improve the accuracy. The time the time is not the time increase not very small. So it can release the the accuracy， 就是看那个release 看那个improve the accuracy and not improve the time.
Okay, cool. No, that's perfect on that one. Okay, so thank you very much for your presentation, and I think we'll move to the next speaker. Yeah, and I believe our next speaker will be online video as well.
Hello, I'm Chen. Today we are going to talk about our journey to understand how to bring contour delineation process of medical structure into virtual reality. To begin with, I would love to introduce the procedure of today's radiotherapy treatment planning process. Here, we show the workflow of how a radiotherapy process looks like. From beginning, while patients are taking the CT scans, to eventual stage when the well-calculated radiation energy is successfully delivered to the tumors. Our focus of this work is on the second stage, which is also called contouring, where the oncologists need to delineate and segment the tumors or healthy surrounding tissues. Inaccurate contouring could be dangerous, which could cause tumor recurrence, decrease long-term survival rate, increase long-term toxicity, or even death. In today's hospital, such process is typically supported by oncology software such as Eclipse, which, as you can see here, only works on 2D display. The setback is obvious. It is less intuitive and requires high task loads to complete the tasks. Extended reality could be promising for such healthcare applications due to the benefits of 3D immersive environment. However, how could we leverage such affordances and bring contour delineation into VR? To address this, we conducted a 6-month iterative design process, including a preliminary needs finding, an initial prototype design and evaluations, prototype enhancements, as well as final re-evaluations. We invited 3 domain experts from UCSD Health Systems at different experience level, including a first-year medical school students, a resident, and also an attending doctors. So all participants do not have prior VR experience. While we gathered a lot of insights with domain expert participants, one of the most important findings that we would love to share is that participants think inspecting medical structures in 3D might be super helpful, yet the precision contouring is indispensable. However, ironically speaking, precision annotations in 3D immersive space is challenging due to a lack of depth perceptions and physical support. To address this, we adopted the design ideas that attempted to integrate pen and tablet interactions into extended reality, such as Pinta, which combines the benefits of immersive and precision drawing. At the end, we decided on using Logitech VR stylus as well as the Trackit tablet as the input tools. Inside virtual environments, participants could see the photorealistic images and an enclosed blue box indicating the physical annotation areas. We then defined 4 design spaces based on the dimension of information input and consumptions. More specifically, the process of information consumptions allow participants to observe and inspect the medical structures and contouring results, whereas the process of information inputting enables users to interact with medical structures as well as drawing annotations. Notably, The dimension for consuming information must not be lower than that of information inputting. Therefore, we rule out this possibility. We then implemented all design conditions using SteamVR and HTC Vive i Pro. The first condition is a baseline, which emulates today's contouring process on a 2D display-based desktop environment, where the participant can scroll mouse they could scroll the slides by scrolling the mouse and contouring using the keyboard and mouse. In the second conditions, participants could inspect and annotate the medical scanning slices on a handheld tracked tablet. However, during this case, the 3D visualizations and interactions are disabled. Next, we enable participants to inspect the medical structures in both 2D and 3D, which we consider this as the cross-dimensional. But in this case, they can still only contour on 2D. Finally, beyond the third condition, they can also contour in 3D directly. And after that, they can refine the contours on the 2D handheld tablets. To understand and evaluate the performances of the defined design conditions, we set up our systems in an office room using 3 base stations. To evaluate the contouring performance of each of defined design space, we recruited 8 participants who have the basic anatomy knowledges of the designated contouring task, yet do not have skills of interpreting 2D medical images. The goal here is to minimize the impact of the 2D medical image interpretation skills as a potential confounding factors. To the end, we selected 4 contouring tasks contributed by 4 anonymous patients with domain expert participants from the preliminary exploratory study. As for 3D visualizations of medical structures in VR, we use direct volume rendering and pre-tune the rendering parameters with a professional oncologist to make sure the target is clear and visible to the participants. We then design a 3-phase procedures where the participants will first complete our pre-study questionnaire, contour each of designated 4 cases using 4 defined conditions where the order of the testing conditions has been counterbalanced. Participants will finally complete a post-study questionnaire as well as a semi-structured interview. To quantitatively evaluate participants' performance, we use the measure of dye similarity coefficient, which has already been widely used to evaluate the contouring quality in oncology educations and practical RT treatment planning process. We also measured and evaluate the time for initial explorations as well as task completion time. For the final 2 conditions, which requires participants to interact with 3D medical structure, we also measure the attentions by tracking the real-time eye gaze. Our first evaluation results demonstrate that the visualizing of 3D medical structures can increase the contouring precision, although the capabilities of annotating 3D directly does not yield significant precision gain. When it comes to temporal measures, While no statistical significances were observed, all participants can locate the target within 1 minute and finish the designated contouring task within 10 minutes, with the support of inspecting in 3D and contouring on 2D plan. So whether the count 3D is actually useful, our results on attention evaluation provide a positive answer. As seen here, especially during the initial stage for both C3 and C4, participants heavily rely on the 3D visualization to find the target. However, during actual contouring stage, they still rely more on the mirror slices on the handheld tablet. While we gained a lot of insights while discussing with domain expert participants, we would like to highlight our findings in terms of 3 aspects. Firstly, participants believe that the capability of inspecting 3D medical structure could be helpful. For example, P7 emphasized the importance of providing bigger picture and reduction of the cognitive load. However, some participants also mentioned the needs of 2D support for inspecting the target detailed structures. So for example, P2 mentioned that the failures of inspecting inside the body and the 2D mirror slices could be super useful for inspecting the detail of medical structure. In addition to that, some participants also mentioned the challenges of precise 3D drawing directly inside the virtual medical structure. Lastly, I would love to conclude our work in terms of 3 aspects. First, we explore the VR contour and attempt to address the key question: how should we really bring the contour delineation into VR? Second, we conducted a preliminary user-centered iterative design process with domain expert participants to explore the potential design spaces. And finally, through within subject study, we showed that the inclusion of 3D visualization could increase the contour precision and reduce the mental load, frustrations, as well as overall efforts. We hope our work could be beneficial to future research in designing VR-based medical software for radiation oncology and beyond. Thank you so much for the time, and please refer to our paper for more detail.
Thank you for the present. Now we'll open it up to the floor. Do we have any questions? Yeah, one at the back there.
Hi, Xuan Hui from UCD, and thank you for your presentation. It's very interesting work. So I have very little questions. So in the experiment design, you used the 2D and 2D for the baseline assessment, right?
Yeah, that's a. Oh, have you finished?
So basically, why don't you just use the playing a laptop to achieve that, but instead you achieve that using the immersive environment? Because to my knowledge, the user may not be able to see the keyboards and the mouse. Would that be an influence to the experiment result?
Okay, yeah, so I think that's a great question, actually. So initially, we actually tried using the just regular 2D display-based desktop. However, one interesting phenomenon we found is that most of residents and also medical school students do not have any prior experience of using VR. So what happened is that after they wearing the VR, wearing the head-mounted display, they are not comfortable. And I think like majority of us will know that, will have feeling of that. And such uncomfortableness can actually highly degrading the general user experience and introducing an unnecessary confounding factors. So the key question that we are trying to explore in this work is really about whether 3D immersive environment can help the contouring delineation process in radiotherapy treatment planning in some way. We are not really interested in focusing on like how uncomfortableness of the VR head-mounted display can degrade in the contouring experience. So in order to minimizing these confounding factors, we kind of mimic the experience of 2D display-based contouring, but inside the VR. So we admit that they will feel that's comfortable, right? However, in this way, we can really diminish the confounding factor of the comfort of the uncomfortableness introduced by the head-mounted display. So basically, in all conditions, they are all wearing the head-mounted display. So this is not comfortable, so we admit that. But what we are really focusing on is really the differences. And such differences could really draw huge insights for future design of head-mounted display-based VR, head-mounted, like VR-based contouring in radiotherapy treatment plan. And honestly speaking, it is a setbacks. Basically, today's most of head-mounted display, including the HTC Vive we are using, is not comfortable. But we hope like in the future, when people can make the head-mounted display more comfortable, more ergonomic, and then whatever we unveiled in our work can really apply to there. So it's really about long term. But for this paper per se, the reason why we are choosing to design the whole study in this way is really trying to minimize the impact of the confounding factor created by the uncomfortableness of the head-mounted display. Yeah,
Okay, thank you very
I
much.
hope that answer your
Yeah,
question.
Yeah, thank you.
No.
Thank you.
And thank you. I think we're going to have to move to the next presentation to keep on time. So just a round of applause again. And our next speaker is going to set up. Our next two presentations will be in person.
Hello everyone, my name is Naoya Fukumoto, and I am from Cymatics Theory Engineering Laboratory at Nara Institute of Science and Technology, Japan. The title of today's presentation is an object synthesis method to enhance visual haptic consistency. Normally, we manipulate virtual object with a VR controller. However, its shape is different from the shape of the virtual object. For example, on the left, you have a virtual gun. On the right, you have a virtual sword. But we always feel the sense of touch through the same VR controller. As a result, the actual sense of touch you feel is different from what you expect from appearance of virtual object. This difference is referred to as a visual haptic inconsistency. To address the problem, many haptic devices have been developed. However, it is difficult to provide high degree of freedom with arbitrary shapes. In addition, such haptic devices are generally large, require special equipment such as an air compressor, and they can't be attached or detached by the user themselves. So such haptic devices are not always suitable for casual use. So we propose to use real object around us that has a similar shape as a haptic proxy for the target virtual object. For example, we can use an umbrella as a virtual golf club and a tennis ball as a virtual apple. They are expected to produce more consistent haptic sensations than the VR controller. However, haptic discomfort may still occur due to visual haptic inconsistency. This is because the shape of the real object is not exactly the same as that of a virtual object. In this study, we propose a chimera object, alternative virtual object, to improve visual haptic inconsistency. A chimera object combines the shapes of real object and its corresponding virtual object. Then, we report on the user studies that demonstrated the effectiveness of a chimera object. Finally, we propose an interactive chimera object creation system for end users, and report on another user study that demonstrated its effectiveness. I will now describe the chimera object in more detail. The shape of the chimera object is generally identical to that of the virtual object. Only the part of the chimera object that the user will touch is deformed to that of the real object seamlessly with no visible seams. In this way, the chimera object will be visibly similar to the object but original virtual object, while its appearance where the user will touch is consistent with the real object. A chimera object is a synthesis from the virtual object and a 3D reconstructed real object. At first, we subdivide each triangle and resample the vertices of the two objects to regulate the vertex density. Then we perform a principal component analysis for each object, and then align their origin and axis so that all vertices are represented in the same coordinate system. Next, we find vertex matching between the two objects so that every point on the real object has corresponding point on the virtual object. Finally, we generated a new vertex of the chimera object between each vertex pair with some weight, and we create its surface using person surface reconstruction. The parties of the chimera object are closer to the real object for the part the user will touch and closer to the virtual object otherwise. We evaluated the effectiveness of the chimera object in the effect of reducing haptic discomfort. In this evaluation, we measured the sense of haptic discomfort experienced during two interactions. One with object is an unprocessed virtual object, and the another with the same real object and corresponding chimera object. We expected that the participants would feel less haptic discomfort with the chimera object. We modeled the tiller to examine both dynamic touch and static touch. A dynamic touch is generated when a prevailing motion is applied to an object. Static touch is generated on grasping an object without hand motion. Participants will touch the dagger tip to experience dynamic touch, while grasping its handle to experience static touch. To give a variety of the level of visual haptic inconsistency, we created 12 different real objects by using 3D printer. As shown on the left, they created combination of 4 types of tip shapes, that is, ideal, sharps, round, and chamfer, and the 3 types of handle radius, 10 mm, 15 mm, and 20 mm. 12 chimera objects were synthesized for each real object as shown on the right. Next, I will explain the experimental design. Participants were asked to wear a head-mount display grasping a handle of the real object with their dominant hand and touch the tip with their non-dominant hand. After 1 minute's experience, they were asked to answer a questionnaire on visual haptic consistency and repeat that task for all the 12 real objects. They performed the produce in 2 conditions. In original conditions, they always saw an original virtual object. In chimera condition, they saw each of the 12 chimera objects corresponding to the real object they were manipulating. 8 male participants in their 20s participated in evaluations. This figure shows the real level of participants' pervasive visual haptic consistency. The left figure is about the static touch and the right figure is about the dynamic touch. We found statistically significant difference when the handle radius was 20 millimeters and when the tip shapes of the chamfer and round. In these conditions, a chimera object reduced the haptic discomfort. However, When the tip shapes of the sharp, they felt less consistency with chimera object. This is probably because person surface reconstruction sometimes produces a rough surface. No statistically significant differences were found in other conditions. So overall, these results show that the chimera object improve visual haptic consistency. So far, the experimenters has determined the weight distribution of the chimera object. However, optimal weight distribution will depend on each individual. We believe that the user in the loop framework is very important for the success of the chimera object. Therefore, we propose an interactive chimera object creation system for end users and evaluate its effectiveness. We implemented user interface that allows the users to assign deformation weight to each vertex of a chimera object. To specify the weights, the user can paint an object on grayscale from 0 to 1. The brighter the pixel values, the more similar that the part is to the shape of the virtual object. And the darker pixel is the value, the more similar to the shape is to the real object. Here we show a chimera object creation system in user. The figure on the left shows the graphical user interface is in which the user can specify the weights by painting the object directly or interpolating the two specified points at once. The figure on the right shows how the user sees a chimera object in VR. The user adjusts the weights and confirms the chimera object in VR until he or she is satisfied. We investigated the effectiveness of the chimera object creation system. In this evaluation, we asked participants to create a chimera object in 10 minutes from the given models. 8 participants are there 20 participants in the evaluation. Results suggest that the visual haptic consistency is improved with the chimera object, and that system usability scale scores are about 69, which is comparative to SES standard score of 68. Please check our paper for more detail. In this study, we proposed and evaluated chimera object. Chimera objects complemented haptic sensations when we use a real object around us as a controller. Our first evaluation confirmed that the chimera object improved visual haptic consistency. We also proposed and evaluated a chimera object creation system. It supports chimera object creation by iterative weight adjustment and in VR confirmation. Our second evaluation confirmed that our system allows novice end users to create user-satisfied chimera object with a moderate usability. Thank you for listening.
So we have a brief bit of time to open to the floor if there's any questions. Yeah, one at the back there.
Yeah, thanks for the presentation. Mine is not a question, it's more of a clarification. So in your camera object, where was the placement modular placed? I mean, you had this we have the controller. So where exactly was the controller placed when you were using the actual object?
Sorry, once again.
So you basically have this camera object, which is replacing the controller, which the person would be holding. So where was the controller placed on this camera object? Was while using this real object, this real camera object, was the person actually using the controller?
I think he's asking where you put the Vive tracker on the top.
Do you mean how to track the object?
Yeah. So the 3D object, I assume you put a Vive tracker at the top or used a tracker so they were able to hold the 3D object?
Yes, in this research, we need to set a tracker to the real object, but future work, that is, we will reserve it.
Okay, thank you.
Okay. Any more questions? We have time for a very short question yet. So go in there.
Thank you for interesting presentation. I think it's in the context of hand video erection, it is known that the shapes of the edges are really important because I think it's difficult to transform. It is difficult to use cube as the replacement of the sphere because they use a few edges when grabbing. So I think there are some restrictions on which you can apply this camera object method, and I want to know the other limitations about using your method. Does this make sense? So,
thank you.
In which conditions can you create a camera object?
Which condition do you mean?
So,
wait.
Can you put the slide? Yeah. You show the laptop again?
Yes, the second examination, we make the camera object for this. And for example, the task B, banana and gun. Banana is a real object, and virtual object is a space gun. That is, for example. So that is not for good at detail, correct detail, but the
general shape is.
Yeah, I'm afraid we have to finish up. You guys can keep talking at the coffee break, I think.
Yes, thank you.
Cool. Thank you very much on that. That was a really great presentation. Really interesting idea. So we have our final speaker for today. And we'll just get Alexei here will talk to us. If we're all good. Yeah. Yep. All good to start?
Yeah.
Yeah. Waiting on the laptop. There we go.
Yeah. Hello, everybody. My name is Alexei, and today I'm presenting our paper exploring efficiency of vision transformers for self-supervised depth estimation. Let's start with the definition of the problem. A monocular depth estimation is a task of the estimating distance relative to the camera for each pixel of a RGB image. And there are several applications of depth estimation. First of all is augmented reality and self-drivings and also 3D scene reconstruction. And next, let's move to training process of depth estimation. For monocular depth estimation, there are two variants, supervised and self-supervised. In supervised case, we directly learn ground truth, and for training we need both images and ground truth depths. And for self-supervised, we can train model using only geometrical constraints, and for training we need only video or stereo pairs. Oh, sorry, yeah. Oh, sorry. Yeah, now it's better. Yeah, sorry. By the way, for in supervised case, performance is better, but for supervised step estimation, we need a lot of ground truth data, which is hard to obtain. And for self-supervised approach, we need only images, or videos, or stereo pairs, and it's much easier to scale data set. And let's look closer on self-supervised estimation, as I said, we have to. If we have two views of one scene, we can, using depth and relative pose, to estimate one view from another by predicting warping. And if we look closer on loss functions, as I said, we can use depth, relative pose, and some camera parameters. And from source view, predict estimated target view, and then compute loss between target view and estimated target view. As loss function, we use structural similarity index and L1 loss. And also we add smoothness to smoothness realizations. And the main point of the paper is exploring different architecture for self-supervised depth estimation. In previous works, authors mostly used fully convolutional networks, which have only limited receptive field, and we presented several new architectures based on combination of vision transformers and convolutions. And all these models have global receptive field. And let's look closer on our architecture. As I said, as one encoder, we use fully convolutional encoder. It is a usual ResNet. And for vision transformer, we used encoder with firstly split image into a sequence of patches, then project the patches in tokens, and finally we pass this sequence of tokens through a common transformer. And about decoders, fuse and upsample features from encoder in previous stage of decoder, and one decoder is fully convolutional decoder, and the second decoder is combination of convolutions and transformer. And in transform decoder, we first apply convolutions for input from previous stage of decoder, and then compute attention between encoder and decoder features. And let's move to our experiments. In our experience, we use two data sets. First of all, it's a Kitty data set, and the second is New York data set. It is most widespread data sets for the estimation for outdoor and indoor scenarios. And about metrics, the first metric is mean absolute relative error, and this metric is low is better, and the second metric is accuracy, is defined as a percentage of the relative depth prediction within threshold. And in our first experiment, we try different combinations of encoders and decoders with different combinations of convolutions and vision transformers. As you can see, the best model contains the vision transformer encoder and convolution decoder. And based on these experiments, we try to improve models by changing parameters of encoder and decoder. And as you can see, on Kitty dataset, we outperform all previous models in self-supervised case. And we also obtain the similar results on New York V2 datasets. And let's look on quality comparison. As you can see, vision transformer model predicts better depth for small objects like people and roadsides, and also for hard structures like leaves or nets. And next results on New York data set, it is the same. Our models predict better and more global consistent results for long objects like sofa, for example, and more accurate depths for small objects in bathroom. And finally, we compare inference time and complexity of our models. And in theory, our models with vision transformers have less complexity, but they demonstrate better error compared to full convolution models. But on GPU, it was V100. Our models slightly slower than full convolutional baseline, but it still works in real time. To conclude, our main contributions is novel neural network based on combination of vision transformers and convolutions, and our model demonstrates better performance at poor convolutional baseline, and we achieve state-of-the-art metrics. In future work, we plan to adapt proposed models for AR application. Thank you for your attention. If you have any questions, I will be glad to answer them.
So I'd like to open it up to the floor if there's any questions. There's our roving mic. Questions? Any questions from the floor? Just like follow on from previous questions asked, what would you see as sort of the future applications of this technology? Is there any sort of use cases that you feel this is perfect for?
I think there are two perfect applications, as we discussed today a lot. Depth estimation for air, usually used depth sensors, and we can replace depth sensors by monocular depth estimation models. And of course, also depth estimation models is very useful for self-driving cars.
Okay. And you have answered a question.
Yeah.
Over a decade ago, I had a machine vision specialist in a startup with me, and he claimed this would never be done. So I'm very glad to see this research. In fact, I might email him your paper, go, look, I wasn't crazy on this sort of thing. And I know there's other algorithms that have been doing this since then as well, but this seems to be getting to the new state of art and using new techniques, which is fantastic. So yeah, I think we're going to close out the session then, and we will pass on to the next session. So thank you again.
Thank you.
And thank you again to all of our speakers.
All right, hello everyone. My name is Gerald Thomas from Virginia Tech. I'll be serving as your session chair for the audio and haptics session. We have 6 papers today. I got the chance to look at them a bit last night. I think we have some really good ones. I'm excited to hear what the presentations have to say. Each presentation or each paper has 15 minutes total, 12 minutes presentation, 3 minutes for Q&A. For those presenting in person, I'll give you a 2-minute warning as you approach your 12 minutes. And then for those people watching online, I am keeping an eye on the chat in Zoom, and I can relay any questions you might have. Oh, and then as we're presenting during the Q&A, if you are the next presenter and you're an in-person presenter, please come up to this table so we can smoothly get you on the stage and keep this going quickly. With that said, our first paper is Tape Touch, a handheld shape-changing device for haptic displays of soft objects, presented by Lifeng Zhu online, and he'll be around for questions afterwards.
Hello, everyone. I'm very happy to be here introducing our work in ISMAR 2022. My name is Li Fengzhu. Me and my collaborators Xu Dongjiang, Jiang Weishen, Hen Zhang, Yiting Mo, and Aiguo Song are from Southeast University, China. I will talk about our work Tape Touch, a handheld shape-changing interface for haptic display of soft objects today. This is a work about haptics. For virtual reality or augmented reality, users get really high-quality visual feedback now. More than seeing the virtual contents, users also expect to touch and feel the virtual objects to be better immersed in the mixed reality world. To make it happen, researchers have been actively working on haptics to enable realistic force feedback. Typical haptic devices can be classified as grounded or portable devices. Grounded devices are more powerful in producing rich haptic feedback. For example, by pushing pins to reform shapes, pin-based haptic devices are good at rendering shapes. However, for a fine-scale rendering, it demands a lot of actuators and is hard to make them small and portable. Under the challenges to make haptic devices portable, researchers developed various solutions in the form of handheld devices or wearable devices. However, according to our literature review, existing portable devices cannot well support both shape and softness feedback. In this case, our goal is to develop a handheld device, which is portable. With the device, we hope users can feel the shape of the virtual objects or perceive the softness of the virtual objects by touching. To this end, we propose Tape Touch, a handheld shape-changing device for haptic display of soft objects. Our key idea is to actuate a brass tape. By changing the shape of the brass tape to fit the virtual objects, users are expected to feel the shape. And the material property of the deformable tape can also be presented to the users. Based on the idea, we designed the structure of Tape Touch with 4 motors as actuator, a brass tape as a haptic media, and several adapters to connect them to user hands. Users can hold or wear Tape Touch to get haptic feedback. Here, we illustrate the working principle of Tape Touch. Motor 1 and Motor 2 are actuated to control the translation of the 2 ends of the tape. Motor 3 is attached to the translational platform actuated by Motor 1. When it rotates, we control the angle of the brass tape at one end. Motor 4 works similarly to rotate the other end. Now we are ready to design the signals on the motors, so that the deformed tape provides the haptic feedback corresponding to the surface shape of virtual objects. We use abacus to simulate the deformation of the brass tape under different boundary conditions. By collecting the simulated data as training data, we adopt a multi-layer perceptron to learn the regression from the produced shape to the control signals. The data-driven method works well in our application. We show several fitting results of our method here. Here, we illustrate the large shape space rendered by Tape Touch. Although the brass tape does not render concave surfaces directly, we may track the position of the Tape Touch and change the height of the tape dynamically to provide the experience of touching more complicated shapes. Tape Touch is also capable of rendering softness. In this figure, the bent tape in the form of the blue curve is perceived stiffer than the green one. We simulate the deformation to study the force displacement curve of the bent tape under fingertip pressure. The perceived stiffness is plotted and used to control the rendered softness. We test tape touch to render shapes and levels of softness. The user here touched the head, lung, and ear models displayed in the VR scene. Tape touch was able to change its shape to fit the touching surface. In this scene, the user was touching a stiffer sponge and a softer sponge, respectively. Tape touch reproduced different levels of perceived stiffness by controlling the deformed tape. In this demo, the ball bounced back to different positions, and the tape touch dynamically updated to provide the corresponding haptic feedback to the palm. We conducted a user study to evaluate the shape perception with tape touch. In this study, the participants were asked to identify the shape, what they felt, provided by tape touch. We randomly displayed 10 different shapes and collected the results. As shown in the confusion matrix, we find the shapes rendered by tape touch are distinguishable and have a high recognition success rate. In terms of softness perception, we rendered the shape with 4 levels of softness in a random order, and participants pressed and sorted the shapes according to their perceived softness. We collected the results and listed the successful sorting rate in the table. We also studied the VR experience with tape touch. Participants could see the virtual objects and touch them freely in this study. For the shape feedback, we compared tape touch with vibration-based shape feedback on a 7-point Likert scale to collect the subjective evaluation. The results shows that the shape rendered by tape touch significantly enhances users' VR experience compared to the vibration feedback. Similarly, we also evaluate the VR experience for the softness feedback. We compared with vibration-based softness feedback, in which harder objects lead to higher vibration frequency and magnitude. The subjective feedback shows that the softness rendered by tape touch significantly enhances users' VR experience compared to the vibration simulation. In summary, we propose a new shape-changing interface based on deformable tapes for haptics. As a first step to demonstrate the new shape-changing interface based on deformable tapes for haptics, we believe the approach could be improved for more powerful functions. We need to work on directly rendering of more general surfaces. It is also interesting to explore the relationship between shape and softness of tape touch. We may provide more tactile feedback by replacing the brass tapes with different materials or adding heat control. By improving the structure design, it is also possible to work for more complex contact, such as grasping. In this work, we use a data-driven method for controlling tape touch. We will also study how to adopt inverse dynamics for controlling the deformable tape. Thank you for your attention, and I will be happy to take any questions. Thank you.
All right, thank you, Li Feng. That was a great talk. Do we have any questions?
Thank you very much for the very interesting talk. I was just wondering if you can somehow extend your work to represent a more flexible 2D surface. It looks like more 1D in your country, but do you have any ideas?
Yes, thank you for the great question. Actually, at the beginning, we already think about how to produce the 2D feedback. Our key idea is for this tape touch paper, our key idea is to extend the like the point-based, pin-based devices with this curve-based devices so that we can extend the point to like 1D curve. So a very natural idea is to think, is it possible to really compare with the pin-based devices with 2D shape-changing interface? So a very straightforward method is to using maybe maybe a lot of these tapes we can weave them together to form a 2D surface. And in this case, we still need a lot of actuators to make it happen. So for our purpose to make a holdable device or wearable device, so it is still challenging for us to make a miniature design. That's why so far we still gave our first trial on this 1D type haptic feedback device. So we will also try to work on these 2D cases. Yeah, thank you for your question.
Thank you very much. That's exciting. Looking forward to see your new work next year.
Yeah, thank you.
All right, any other questions?
Hi, my name is Agustin. Thank you for the presentation. Have you considered using the object like closing the loop, in the sense you introducing some kind of pressure or pushing the object and introducing some kind of like, closing the loop of interaction, using it to actuate basically?
Yes, this is a really great question. This is actually, we have not think about that before. So far we still use an open loop control for the objects. So if we are going to close the loop, we need to add some sensors. I guess we need to maybe using some third person view to observe the shape, so that we can do some closed loop control. Yeah. This is a great question. So we do need to think about it. If is there any compact way to install more sensors on the device? In this case, I guess we may also provide more, if we can add some force sensors, we can also maybe provide some controllable forces. Yeah. Thank you so much for the suggestions. Thank you.
Yeah, that would be really exciting. Thank you.
Yeah,
All right,
thank you.
We have time for one more question.
Hello, Jeroen Seys from Hasselt University speaking here. Thank you for the interesting talk. It was really good to see this kind of work on haptics. Congratulations with that. I'm just quickly wondering, what is the average amount of speed that is actually, or the average amount of time that's necessary to change shape for this current device?
Okay, yeah, thank you for your question. So actually, the response time composed of the the computational time to find the signals, and then another part is from the motor. So far we do not use high-end motors. So the most delay they might from the actuators itself. For the computational part, it is very fast. I think it's less than 20 milliseconds. We can find the control signals, which control signal we should send to the motor. So if we have some better high dynamic motors, I think it can be faster. Yeah. So far, we expect to touch some objects with continuous change, so it works well in our tests and experiments.
All right, very excited to see that moving forward. Thank you.
Thank you. Thank you so much.
All right, let's give the presenter one last thanks. Thank you again. The next paper is Auditory Feedback to Make Walking in Virtual Reality More Accessible, presented by M. Russell Mahum.
All right, good afternoon, everyone. I'm Russell Mahmoud. I'm a PhD student from University of Texas, San Antonio. I'm very happy to share my research work, Auditory Feedback to Make Walking in Virtual Reality More Accessible. First author for this paper is myself. Michael Stewart and Dr. Alberto Cordova is from Department of Kinesiology, and Dr. John Corliss is my PhD advisor. All right, let's start with some introduction. Virtual reality techniques are becoming more popular in many sectors like rehabilitation, education, and entertainment. However, VR causes imbalance and gait disturbance issues for healthy users, which is severe for people with disabilities. For example, people with multiple sclerosis, because those people have already some balance or gait disturbance issues, and additional gait disturbance by VR makes it impossible or nearly impossible for them to get benefit from consumer VR applications. For this study, we evaluated effects of different auditory feedback on gait in virtual reality. The purpose of this work was to make immersive VR more accessible in terms of walking. The motivation behind was that there are a lot of work that confirm there are gait disturbances in VR, but we found minimal work had been conducted to reduce this effect. Also, most previous research was focused on users without disabilities. However, in our study, we included participants with mobility impairments, also participants without mobility impairments. Most of the rehabilitative approaches to improve balance and gait in virtual reality didn't use head-mounted display or only constrained to seated tasks. In our study, we included head-mounted display and evaluated standing tasks. We evaluated basically 3 kinds of auditory feedback: spatial, rhythmic, and static rest frame, which was found to be effective in prior real-world environment. We recruited 39 participants in total. 18 of them are with mobility impairments, and 21 participants are without mobility impairments. We had 5 conditions. First condition was baseline without VR to measure their gait in real world. We had 4 different VR conditions. First one is a spatial auditory feedback, which was basically a specialized audio from Unity 3D. We used Google Resonance Audio SDK for audio spatialization. For this condition, when participant moved from his center position to left or right, the audio volume increased, and participant got a better feedback that he's swaying from his center position. For the static rest frame audio, which was a static uniform white noise played from Unity 3D via head-mounted display headphones. Rhythmic audio was similar as the static rest frame audio, but it was played at every 1 second interval. For no audio condition, we didn't provide them any auditory feedback in VR, but still they used the head-mounted display to make it consistent with other conditions. Oops, sorry. These are the real and virtual walking environment. The left figure shows the real world environment, which is a real gait ride that is placed in our lab. The right figure shows the virtual environment. Participants are able to see the virtual gait ride via head-mounted display. And again, the left figure shows the real world walking, where participant is walking on the real gait ride. For the right figure, which is virtual environment walking, participant is still walking the real world gait ride, but the virtual gait ride was displayed by head-mounted display. For our study procedure, we first introduced the participants about the study. Then participants signed the consent form approved by IRB. Then participant completed the COVID-19 screening form, ABC scale form, pre-session simulator sickness questionnaire. After that, we attached participant to the harness and suspension system to protect them from falling. We then started the real-world walking. We had 3 trials. Then they started the VR talks, where we had 4 conditions: spatial, static rest frame, rhythmic, and no audio. For each condition, participant completed 3 trials. So each participant completed 15 trials in total. At the end of the study, participant again completed post-session simulator sickness questionnaire form and a demographic questionnaire. Finally, we paid them $30 per hour. For our study, the auditory feedback are counterbalanced to reduce the learning effect. Participants are allowed to take rest between trials if they needed to, because a lot of them are without mobility, with mobility impairments, a participant with multiple sclerosis, so they had reduced physical ability. The whole study took around 1.5 hours to complete. IRB at UTSA approved the study. We had 3 different kinds of metrics in our study. First one is gait metrics. We measured the major gait parameters, for example, walking velocity, cadence, step length, stride length, step time, cycle time, and swing time. We also administered the ABC scale, which is a 16-item questionnaire used to measure participants' physical ability. Then the last one was simulator sickness questionnaire, which is also a 16-item questionnaire to measure the increase in cyber sickness. For statistical analysis, we applied Sapir-Whorf test to see if the data is normal or not. We found the data are normally distributed. Then we applied 2x5 mixed model ANOVA to find if there is any significant difference between the conditions. Where we had 2 between subject factors. One is participants with mobility impairments, and another one is participant without mobility impairments. We also had 5 within subject factors for the 5 study condition. When we found a significant difference from the mixed model ANOVA, we applied the two-tailed t-test to find the specific difference between any 2 study conditions. Also, for measuring the cyber sickness, we applied two-tailed t-test to the pre-study SSQ scores and post-study SSQ scores. We also applied two-tailed t-test for the ABC score to measure the physical ability for both group of participants. These are the results for the walking velocity comparison. The left figure shows the walking velocity for participants with mobility impairments, where you can see for the VR baseline condition, which is the VR condition without any auditory feedback, the walking velocity was decreased. However, with the auditory feedback, for the spatial, static, and rhythmic, the walking velocity significantly improved, where spatial audio had better performance than others. We also found similar results for participants without mobility impairments, which you can see on right side, where spatial auditory feedback outperformed other conditions. We found around 12 gait parameters to be significantly affected, significantly improved, applying the auditory feedback condition. However, I'm just displaying one of them because walking velocity is kindly directly or indirectly related to other gait metrics. You can see our paper for other results. For the effect size, you can see the spatial audio condition had greater effect than other conditions for both participants with and without mobility impairments. We found few gait parameters in mobility impaired group affected differently, and few gait parameters affected differently for without mobility impaired participants. For example, we saw step time that was increased in mobility impairments participant, but that had no effect for the participants without mobility impairments. Also, in previous study, we found this kind of thing happened. Few gait parameters affected differently for person with disabilities. We also found the spatial audio, which has the greatest result for our study. So we hypothesized if the auditory condition that changes with positioning that might have greater impact than other conditions. We found no significant increase in cyber sickness. As you see, our study environment are very simple, so that might be one of the reasons there was no increase in cyber sickness. To conclude, in our study, spatial, rhythmic, and static rest frame auditory feedback condition improved balance significantly compared to no auditory feedback in virtual reality condition. However, spatial auditory feedback can be preferred over others as it significantly outperformed other conditions. From this research, researchers will be able to better understand how to apply auditory feedback in a head-mounted display-based virtual environment to improve gate performance. It might help developers to create more usable and accessible virtual reality environment. In our future work, we plan to investigate other feedback modalities to improve gate in virtual reality, for example, visual feedback or haptic feedback. These are the references. Thank you.
All right, thank you very much. That was very interesting. Are there any questions on the floor?
Hi, sorry if I missed it. I didn't quite get how the audio feedback work, as in the spatial one. I mean, I'm walking, but then what is it I'm hearing? Is it the footsteps or?
Okay, you mean how the spatial auditory feedback work?
What is the feedback? What is the audio about?
Oh,
I know
okay.
It's white noise.
So basically, we provided spatial audio, different kind of auditory feedback.
Yeah.
From Unity 3D via the head-mounted displayed headphones to the participant. So like, when the participant is walking, the gate right had a center position.
Yeah.
The participant are instructed to walk in the middle of the gate right.
Right, so the sound is like something like in the 3D space right in front of me, or what is the space where the
actually,
sound
we had a fixed spatial condition in the middle of our lab.
Okay.
That was at the right side of the participant. That was
Right.
fixed. But the
is it visualized that as well, the sound source, that virtual point where the audio is from?
Yeah, that was a fixed point. But participant got feedback via the headphones
Yeah.
for the spatial audio or other audio. When the participant moved from the center position to left or right, as it is specialized. Like
Yeah, so they can hear either.
Yeah,
if
the audio volume increased
Yeah.
or decreased.
So my question is the audio source, where the sort of the point where the audio is from, is it also visual? Do they have a visual reference point for where the sound is from as well?
Yeah.
Oh, okay. So basically you can see something, there's a sound, and then when they move left and right, if you, okay, they use that.
Okay, yeah.
And then the rhythmic one, is that also spatialized or just?
No, it was not specialized. For the rhythmic one, it was just a static rest frame audio that is uniform, no specialization. It had no relation to user's position.
But why does
just
it?
a uniform is, because we did that, we found in real world that worked for improving like walking.
So basically just hearing some noise will improve my work.
Yeah,
is that?
because the static, that kind of thing, the static signal, that improve balance in real world studies. Yeah, that was our motivation to, let's see how it works in VR. And we found, yeah, it works significantly. Like,
I don't want to take too much of everyone's time, but I'll probably ask more afterwards.
But yeah,
Thank
you can look at the
Fascinating.
paper. We have specific references for each condition,
Okay.
behind our motivation.
Yeah,
So you
okay,
can just
cool.
go to the reference and you should find that.
Yeah, thanks.
Thank you.
Any other questions? All right, well, let's thank the presenter one more time.
Thank you.
The next paper is titled Investigating the Effect of Direction on the Limits of Haptic Retargeting, presented by Aldrich Clarence.
So sorry, there was a technical issue. Well, hello everyone. My name is Aldrich. I'm from the Human-Centered Computing Department at Monash University. Today, I'll be presenting work in collaboration with my supervisors on investigating the effect of directions on the limits of haptic retargeting. With advances in immersion of VR to high-resolution visual and audio cues, the same immersion is expected of other sensory cues to maintain or even improve this immersion. Our work focuses on the haptics experience in VR. While visual and audio stimuli are sufficient to create an immersive virtual environment, this immersion easily breaks once the user tries to interact and make contact with objects within their virtual environment without haptic feedback. Many works have been done to develop a better haptic experience in VR. In general, there are two approaches to providing haptics. These are known as active haptics and passive haptics. Active haptics pursue to accurately generating the property of an object through actuated devices. For example, its weight, texture, and temperature. These devices are usually handheld, grounded, or wearable, and each device is designed to provide only specific haptic properties such as vibrotactile feedback, force feedback, or texture. Also, this feedback is typically applied to a certain part of the body, such as the index finger, and it's difficult to build one-size-fits-all haptic devices. As a result, these devices are more compelling when used in a specialized domain and use cases. Passive haptics is another approach to providing haptics. To provide haptic feedback here, we can use passive physical objects to represent the haptic properties of virtual objects. Thus, the ability to play around with the object and directly feel its haptic properties without holding or wearing additional devices leads more towards an everyday life-like experience. Prior works have shown that this approach improves the VR experience, primarily through increasing the sense of presence and realism of interactions. While it may be seen as a cheap approach to providing haptics, can we say the same when we have many virtual objects in VR? Does it mean we need to physically replicate the entire virtual environment setup? These two questions raise issues regarding the flexibility and efficiency of adopting passive haptics. So, how can we get the benefits of passive haptics without a one-to-one mapping between the physical and virtual environment? Researchers recently explored the use of perceptual illusions to resolve just that. This is called haptic retargeting, a solution that remaps a physical object to multiple virtual objects. The solution is achievable by applying hand redirection. And here, the technique gradually decouples the virtual hand from the physical hand over the course of a reach. Thus, at the end of the reach, the user will see that they touch the virtual object and feel haptic feedback of the physical object. As the technique draws on visual dominance over other sensory information, the user will compensate for the offset introduced to the hand, thus allowing a successful remapping of misaligned objects. To implement hand redirection gradually, we can apply rotation-based and gain-based hand redirection. Rotation-based redirection rotates the direction of movement, allowing the mapping of physical object to virtual counterparts on the left, right, above, and underneath. While gain-based redirection scales the movement to remap a physical object to virtual counterparts farther or closer from it. Under a certain threshold, the users won't be able to detect the offset applied by both techniques due to the brain prioritizing our visual information over other senses. This, however, comes with a limit. A large mismatch between visual and other sensory information, such as proprioception, can still be perceivable and disruptive. So the question is, to what extent can a physical object be remapped with haptic retargeting without being intrusive to the user experience? Prior works have explored the limits of gain-based redirection for reaching across the different axes. Thus, we now know how far or close a physical object can be remapped without being detected when reaching is performed on each axis. The same limits have also been explored for rotation-based redirection when reaching forward. With the known limits, we can estimate how far a physical object can be remapped with haptic retargeting. However, the known limits of haptic retargeting is incomplete, as it has been mainly explored in one primary direction, which is the user reaching forward. But we can't expect interaction across an immersive virtual environment to be limited to just forward reaches. So, is the proposed haptic retargeting limits applicable across different directions? You might ask why we care about the effect of directions. This is because haptic retargeting leverages visual dominance over proprioception. And while we already know that visual and proprioception information are not weighted evenly, the relative weighting of each sensory information changes across the interaction space. As explored by literature around psychology and rubber hand illusion, our perception towards visual proprioceptive mismatch is influenced by where our hand is across the space. Moreover, the accuracy of each sensory modality is affected by various factors. For example, for right-handed users, reaching around the right-hand space is more susceptible to illusions. Another example is users are less susceptible to illusions closer to the body due to better proprioceptive acuity. This motivates us to look into investigating the effect of directions on haptic retargeting limits, so that we know how to use haptic retargeting across the interaction space without compromising the user experience. We derive our hypothesis based on what was known in the psychology and orbital hand illusion literature. Our first and main hypothesis is designed because the brain processes multisensory information differently depending on spatial position and direction. Thus, we hypothesize that detection of a direction differs depending on the reach direction. We tested more hypotheses, which are discussed in more detail in the paper. So, to investigate this hypothesis, we run a user study where participants will be performing reaches with haptic retargeting towards 8 different directions on the horizontal plane. In each reaching direction, we investigate the application of rotation-based hand redirection, where a virtual hand is displaced in a clockwise or counterclockwise direction over the course of a reach, with different magnitudes tested up to 30 degrees offset. At the end of the reach, the user will be asked whether they detected an offset. Their collected responses from this task are then fitted to a psychometric curve to look into the probability of participants detecting redirection across different hypotheses and which direction. Overall, we see that user can approximately be redirected up to 14.84 degrees, depending on the reaching direction. If they detected an offset, we also measure the user's sense of body ownership with a self-localization task. This also helps indicate the perceived magnitude of redirection. The user will be responding to this task by moving the hand seen towards the perceived position by using a controller that they held with the other hand. To give an overview of the body ownership results, we found body ownership towards the redirected virtual hand remains strong until 18-degree redirection. We discussed the results in more detail in our paper. More importantly here, through the study, our work adds to the literature and completes the potential space of haptic retargeting. The following figure shows a top-down view of the limits of haptic retargeting when performing 30 centimeter reaches with their right hand across different directions. We use our estimated limits of rotation-based redirection, together with Ismaili et al.'s gain-based redirection limits, to map the area physical objects can be remapped to. Each arrow in the figure shows the reaching direction performed. As we see here, the remapping area of each physical object is dependent on the reach origin point, reaching distance, and direction. Moreover, the orientation of the area is also differs depending on the reach direction. In summary, our work shows an investigation of the limits of haptic retargeting across the interaction space. And to the best of our knowledge, our work is the first that shows that haptic retargeting works in a larger range of reaching directions, including reaching forward, backward, sideways, and diagonally. We found that reaching direction affects the detection of hand redirection, but not towards the body ownership illusion. We also found that body ownership of a redirected virtual hand remains just as strong within or close to the proposed detection threshold. However, while we do find an effect of reaching direction, we didn't find a strong effect as suggested by literature for haptic retargeting applications. As haptic retargeting is mainly applied within the user's reaching distance, the size of mapping is mainly similar across reaching directions. Thus, we suggest applying a conservative and consistent haptic retargeting limits across the reaching space. While we complete the knowledge of haptic retargeting across the interaction space, there are many other impacts that will affect the limits of haptic retargeting. While this is not a big part of our results, we did run many evaluations to consider these factors. We found age, VR experience, use of hand, and use of haptic retargeting to influence the detection of haptic retargeting. However, we find gender, vision, and height to have no effect on detecting haptic retargeting. We believe these factors are worthy of exploration for future works. Overall, we believe our results are important to complete the knowledge of haptic retargeting and the potential space of it. Thus, we hope our work inspires future VR applications to leverage haptic retargeting in creating immersive and interactive VR experiences. And that wraps up my presentation. I'll leave my contact details here in the slide, and happy to chat for questions. And also, since I'm finishing my PhD soon, I'm also interested in job opportunities. Thank you.
All right, thank you very much. Are there any questions online or in person?
Hi, thank you for the nice presentation. Just, I was wondering, like, why the height has no effect in retargeting for a reaching task? Because, you know, if I have like more height or longer hand, that might have an effect, or you adjust the height in your research. Like if the participant is higher than others, you adjust the distance or something.
So we didn't run like a full-on study comparing the effect of heights, but for our user study, the users are all seated, and we adjust the seating position so the users are all like having their hand laying flat on the table. So maybe that affects the fact that the height has no effect on haptic retargeting. Again, that's not the focus of this study, but definitely it'd be a great future work.
Okay.
Thank you.
And just another quick question, like you said, like it worked for backward direction, right? So backward means participant is still standard, and when they are targeting like backward, they see like it's going backward, they stood still the same position, or they just move like that?
So they're still facing forward, but they're performing backward, which is as in like going from like far to closer to the body.
Okay, thank you.
Thank you.
Thank you.
Thank you for your nice talk. I'm Keigo Matsumoto from the University of Tokyo. And have you examined the sense of agency and the detection threshold relationship?
I'm sorry, I didn't catch that.
Sorry. So have you examined the relationship between sense of agency and detection threshold of retargeting? Yeah.
Thank you for the question. So yeah, for this study, mainly I'm focusing on the detection of haptic retargeting, which is through 2AC study, whether they detected an offset or not. So as a representative of the self-attribution towards their body, our study focuses mainly on the body ownership illusion and their self-localization towards it. So we didn't test the sense of agency in the study.
Thank you very much.
Thank you.
Up here.
Thank you. Sorry. Thank you very much for the presentation. Rebecca Fribourg from École Centrale de Nantes. I was wondering about the age results. So I know it's not the main result you have, but still it's interesting. And since you mentioned them, I want to ask a bit about it. So I was wondering, so maybe I missed it, but could you tell us a bit about the range, maybe the mean age of participants, and just a bit more info about that, and in which direction, how it influenced the results, in which way, older participants behave, how compared to younger participants. Thank you.
Thank you. Oh, sorry, I didn't catch the last question.
It's the same. Oh, sorry. So it was just like in which direction, so you say there is an impact on the age, but in which way, what is the difference between older participants compared to younger participants?
Yeah. Thank you for the question. So yeah, we didn't actually run a full-on study for that, but I'm using generalized linear mixed model to fit the data and see the effect of age towards the detection of haptic retargeting. Yes, so for our study, we have participants ranges. Again, it's on the paper. I don't fully remember, but I think it's ranges from 18 to 50. And most of the participants are around 30 years old. But then, yeah, it'd be great for future work to explore, specifically having different participants of different age ranges and focusing on that. Thanks.
All right, thank you. I think that's all the time we have questions for. So let's thank the presenter one more time. All right, the next paper is estimating the just noticeable difference of tactile feedback in Oculus Quest 2 controllers, presented remotely by Dixuan Cui. As a side note, Dixuan, if you are online, can you please send Melissa a PM? Thank you.
Hello everyone, my name is Dixuan Cui, and today I am presenting my research paper in this video. So the title of the research is Estimating the Just Noticeable Difference of Tactile Feedback in Oculus Quest 2 Controllers. So I want to start with a brief introduction regarding some of the concepts, and I want to talk about the related works, and then I will introduce the methodology that we have used in the study, and then we'll conclude with the results and our future work. So for the introduction, I want to talk about the just noticeable difference concept. So GND is essential for cases that require special attention to detail, and this can be widely applied in different applications, such as VR training applications and also other simulation applications. It can be used for calibration in user interfaces, and it can provide additional cautions in simulations with high risks. So this can be used to inform users more about different situations. Whenever a user is experiencing a situation that has high risk or being dangerous, by applying the GND value, we are able to provide a different tactile feedback for the users to notify them what exactly is going on. So the focus and the scope for this study is to find positive and negative GND values for the Oculus Touch 2 controllers. We have the 3 different properties for the tactile feedback: the intensity, duration, and also the frequency. In addition, we're trying to find the relationship in between negative and positive GND data. We'll let the participants to compare the differences and also report the results in the VR application. The first concept I want to talk about is the tactile feedback. This refers to the physical response to the user, simulating the sensation of touch and tap. Currently, due to the emerging technologies, there are multiple devices that are able to deliver tactile feedback, such as the controllers, haptic vests, haptic gloves, and also self-made simulators. And it's available to provide tactile feedback on different body parts, such as the feet, back, fingertips, and arms. And past studies have found that tactile feedback has a significant effect in increasing the sense of embodiment to VR users. The second concept I want to talk about is the just noticeable difference. So we have 2 sets of words that were used to describe the minimal level and also frequency that can be perceived by human. So the first one is just noticeable difference in level, which refers to GNDL, and the other is just noticeable difference in frequencies, which refers to GNDF. On the right, we have an image regarding all the previous collected GNDF value ranges. These are studies that I've done on different body parts. There is the study done on the finger, the feet, and the arms. On the curves on the left side, you can see that there are various values and also various ranges for the different body parts, but they all stay within a range in between 2 to 100 Hertz. So the methodology for this study is that we created a virtual reality assembly application by simply putting the gear onto the hollow slot. We have created 2 different sections. The first one is the tutorial section. So the participants can start with this tutorial to get themselves familiarized with the operations in virtual reality. And then right after they're ready, they can press on the red button on the table, which is shown in the first image, and they get into the actual testing sections. So within the testing section, they're required to grab and assemble the 2 gears, and the 2 gears will both provide tactile feedback. One of the gears is going to be the reference gear, which stays the same for all the experimental trials. The other gear is going to be the modified gear that is going to provide different tactile feedbacks based on the conditions that we have set. And in the end, we'll ask them in the application, is the tactile feedback different? Participants will need to self-report themselves by pressing the yes or no button right next to the assembled gears. So there are 3 different conditions in the study, which are the intensity, the duration, and also the frequency. For the intensity value, we have a reference of 0.5 meters over second, and we have our comparing gears with 9 different values from 0.1 to 1.0 meters over second with the incrementing gap of 0.1. For the duration, we have a reference of 0.5 seconds. Comparing gear will have value range from 0.1 to 1.0 second with an incrementing gap of 0.1 second. For the frequency, we have a reference of 100 Hertz, having the comparing gear from a range of 50 to 150 Hertz with an incrementing gap of 10 Hertz. Participants will need to compare all the comparing gears value with the reference gear, and then they will need to complete the self-report so we can use that data to analyze the GND values later on. So as for the measurement, we are finding the 75% correct discrimination threshold, which is the standard threshold in GND studies. Typically, if more than 75% participants found the same differences at an over 75% rate, that would be considered as the correct GND value, and we're trying to use linear interpolation to find that value. So for the study, we found no effects of mass or noise on the controller vibration, and this was confirmed by the post responses of the participants. So after the study, we have found the positive and negative GND values for all 3 different properties. Starting with the intensity, we have a positive GND of 0.128 meters over second. And then for negative value, we have a 0.9092 meters over second. So this GND range can be due to the micronoceptors humans have in glabrous skin, because the center of the hand is very sensitive based on the previous psychological studies. And therefore, participants can sense the difference in the controller feedback with minimal unit variation, as the intensity GND values in this case are relatively low. The second set of results we have is for the duration. We have a positive GND of 0.240 second and a negative GND value of 0.108 second. This is because temporal energy is exceeding a certain amount, and that would decrease the tactile perception. So there's this phenomenon called energy interpolation. Whenever you sense the tactile feedback over a certain amount of time, your sensitivity on the different body parts will be relatively low comparing to a less duration of the feedback. So in this case, temporal energy would be the case for generating this difference. The sensation threshold was not affected by vibration of a duration of less than 0.5 seconds, but gradually decreased with vibrations of more than 0.5 seconds. And the last set of results we have is for the frequency. We have a positive GND of 23.3 Hertz and a negative GND value of 30 Hertz. So in this case, we have found participants have various sense of frequency. And based on previous studies, there were really few data existed for GNDF due to the difficulty eliminating potential properties. So in the previous study, Gall found the GNDF for fingertip stimulation is between 8 to 100 Hertz, because fingertip in general is more sensitive than the palm. Our 75% accumulative GNDF in our study, which is 20 to 30 Hertz, is appropriate in this case. And for our last set of conclusions, we have found a strong correlation for all 3 properties of tactile feedback, which is the positive and negative GNDs were almost symmetrical. This aligns with the previous studies because participants are able to sense in a similar way the difference on tactile feedback with both increasing and decreasing properties. So regarding the reference skiers, whether the tactile feedback difference is positive and negative, they were able to sense a similar amount of gap in between the vibration feedback that were provided onto the controllers. So as for the conclusion and the future work, we have found the 3 sets of different GND values for the 3 different properties. And our future work direction will be focusing on factors that can affect the GND and also the effect of GND on other different factors, such as the sense of embodiment or virtual hand illusions. We would like to conduct more study to explore more regarding the GND so that we can better apply these values into the VR applications. And that will be it for the presentation. Thank you guys so much for listening. And this is the end of the video here.
All right. Unfortunately, the presenter is not able to be online right now, so there will not be a Q&A session for this paper. The next paper is Studying the Role of Self and External Touch and the Appropriation of Dysmorphic Hands, presented by Antonin Chemot.
Okay. So, hello everyone. Good. Okay. So, hello everyone. My name is Antonin Chemot, and I'm happy to present you today our research paper named Studying the Role of Self and External Touch in the Appropriation of Dysmorphic Hands. So, one of the big promises held by virtual reality is the possibility to feel present and to interact from a body which might be totally different from its own. Like, for example, a flying robot, or why not an unicorn. In addition to the potential application for entertainment that this body, that we'll call here dysmorphic bodies, can allow, they can also enable to develop novel and more efficient interactions, but also to alter the user perception and behaviors. However, if we want to obtain these results, it is important to induce to the user a sense of owning the dysmorphic body, which is why in this study, we wanted to focus on finding better methodologies to experience a sense of owning a dysmorphic bodies in VR. So the sense of owning an external body, which has often been referred to as the sense of body ownership, has been introduced for the first time by Bodevink and Cohen using a tactile stimulation methodology, which basically consists, as you can see here, in applying simultaneously tactile stimulation to the external body and to the user body, which is not visible from the user himself. This methodology was later replicated to induce a sense of body ownership towards different dysmorphic bodies. You can see some examples here with a robotic body, a six-fingered hand, or duplicated hands, for example. However, in all these cases, the methodology that was used has an important limitation, which is the fact that it always requires the presence of an external effector in order to, which is often another human actually, in order to induce the tactile stimulation, making this technique less practical and harder to replicate to a larger scale use outside of laboratory. In the rest of this study, we'll call this tactile stimulation methodology specifically when requiring the presence of an external effector, the external touch stimulation technique. One potential alternative to this external touch stimulation technique might be the self-touch stimulation technique, which basically consists of the same simultaneous visual-tactile stimulation, but with the crucial difference that because of, as the participant is applying the tactile stimulation by himself, it does not require the presence of an external effector. So far, this technique has been tested and shown to induce a sense of body ownership towards anthropomorphic bodies, but it hasn't been tested yet towards dysmorphic bodies. So to sum it up, we have on one side this external touch stimulation technique, which has been proved to be efficient to induce a sense of body ownership towards anthropomorphic bodies. However, due to the requirement of an external touch, of an external effector, this technique also lacks of practicality. On the other side, the self-touch stimulation technique is a more practical technique, however, specifically in a dysmorphic context. Due to the difference of morphology between the virtual and real body, we have to introduce an offset between the virtual and real effector position in order to ensure more coherence between the tactile stimulation applied to the real body and the stimulation applied to the virtual body. However, we cannot, during a self-touch stimulation, this offset will also introduce different sensory mismatches in terms of visuomotor, but also visuotactiles towards both the active and the passive hand. And to this stage, we cannot ensure that these sensory mismatches won't have a negative impact on the sense of body ownership induced by a self-touch stimulation. And this is why, in this study, we wanted to answer the following question. Can self-touch be efficient to elicit a sense of body ownership towards dysmorphic bodies in VR? Which is a fundamental question that we need to answer if we want to know if self-touch might be a viable alternative to external touch stimulation technique while showing more practicality and being easier to replicate. So to answer this question, we conducted one user study in which we measured the impact of two different variables on the sense of body ownership. First with the tactile stimulation, comparing the self-touch condition and the external touch condition. Then we are also interested in the impact of the virtual hand appearance, in which we compared an anthropomorphic hand appearance condition and two dysmorphic appearance conditions, including one hand with every finger except the thumb 1.5 times longer than the actual participant finger's length, the longer finger appearance condition, and one block-shaped hand. So we collected data from 24 right-handed participants in an experiment which lasted about 1 hour and was made of 12 sections, comparing different combinations of variables. You can see here the basic structure of one section. I will explain it more in detail just after, but basically it consists in first applying different stimulation to a virtual embodied hand, and then to measure the sense of body ownership with different measures. So at the beginning of each section, participant left hand was embodied with an appearance, virtual hand of appearance corresponding to the appearance condition. Unfortunately, here you can't see the video, but basically, they went through a visual motor task in which they had to mimic the movement of another visual hand that they could see on a screen in front of them, consisting in basic movement, translation, rotation, hand, fingers moving, etc. Then participants went through a tactile simulation in which they had to place their left hand still on the table, which was then to which was applied then a tactile stimulation through a brush, which was attached to a controller for the tracking, and replicated inside the virtual environment. This brush was held either by the participant or the experimenter, respectively in the self-touch and external touch condition. Also, in dysmorphic conditions, an offset was applied between the real and virtual brush in order, as I explained earlier, to ensure more coherence between the tactile stimulation applied to the real hand and to the stimulation applied to the virtual hand. Then, in order to obtain objective measures on the sense of body ownership, participants went through two different tasks which results could have been impacted by the appropriation of different dysmorphic bodies. First, with the safe pointing task, assessing the sense of body location, and then with the pressing task, assessing the impact on the behavior during simple interactions. In this short presentation, I won't have time to explicitly in detail these tasks and their results, but I invite you to check out the paper if you want more information about them. Then at the end of each section, participants answer to a questionnaire made of 15 questions regarding the sense of body ownership, but also of subcomponents that could have impacted the sense of body ownership, namely the agency, the sensation of hand change, and the tactile sensation. So now let's observe the result of this study. So as you know, in this study, we wanted to know if self-touch could be efficient to elicit a sense of body ownership towards dysmorphic bodies in VR. And really interestingly, the result that we observed from both objective and subjective measures indicated that indeed self-touch was always as efficient as external touch stimulation technique in the induction of sense of body ownership. So you can see it illustrated here with the result of the questionnaire regarding the sense of body ownership. So in this graph, you can see the result. Each colors represents the result of different appearance conditions, anthropomorphic, longer finger, and block appearance conditions. And for each couple of plots, the left one represents the result of the self-touch, and the right one of the external touch stimulation condition. And what is interesting here is the fact that while there is significant results between each appearance conditions, there is no significant results between each stimulation condition when presented under the same appearance condition, meaning that self-touch was never significantly less efficient than external touch stimulation technique in the induction of a sense of body ownership. An other interesting result that we obtained was this result regarding the tactile sensation, which basically reported the perception of realism during the tactile stimulation. What we could observe was the difference between self-touch and external touch stimulation was significantly higher under the block appearance condition compared to the other appearance condition. And one of the main hypotheses that we have to explain this difference of patterns, mostly between two different dysmorphic conditions, so the longer finger and the block appearance condition, is the fact that these two different appearance conditions actually induce different nature of haptic retargeting, a movement rescale for the longer finger and the movement redirection for the block appearance condition, which later one could have induced a more negative impact on the tactile sensation and might be important to take into account in future utilization. So to sum it up, in this study, we wanted to know if self-touch was a viable, practical alternative to external touch stimulation technique for the induction of a sense of body ownership towards dysmorphic bodies in VR. In order to answer this question, we conducted one experiment in which we compared the sense of body ownership induced by self-touch and external touch stimulation under 3 appearance conditions, 1 anthropomorphic and 2 dysmorphics. And the main results that came out from this experiment is the fact that self-touch is indeed a viable, practical alternative to external touch stimulation technique for the induction of sense of body ownership towards dysmorphic bodies in VR. So now let's finish with just some interesting research perspectives remaining after this walk. First, we thought that it would be interesting in a future study to evaluate a wider range of types and magnitude of body dysmorphism in order to study their impact, but also, as mentioned earlier, the impact of the movement retargeting that they induce on the tactile sensation, but also on the overall experience. In addition, in this study, we wanted mostly to focus on a theoretical validation of self-touch compared to external touch. And however, in the algorithm that we provided, the tactile stimulation was restricted to only one specific area of contact, and specific tactile to one point of contact at a time, and specific areas of contact. In future study, we consider that it would be important to provide to provide a more flexible algorithm that would enable an unconstrained self-touch stimulation. So that's the end of my presentation. Thank you very much for your attention, and I stay available to answer any of your questions. Thank you.
Thank you very much. Are there any questions? All right, there's a couple. I think the lady up in this front row was first.
Hi, thank you for the talk. It was quite interesting. Sorry, my name is Sasha and I'm from Bournemouth University studying phantom touch, and also I kind of find your ideas quite curious with regards to body ownership. So my question is, with the method and the study that you did, do you think your results or your method can actually relate to the dysphoric bodies that are actually used? So for example, if we look at like the metaverses that exist now, if let's say the avatar is, I don't know, a cat with paws, or if there are claws or something that doesn't actually relate anything close to a hand like in your study, do you think that your methodology will still be relevant or would work? Yeah.
Thank you very much for your question. So I guess this is to be honest, this is the first step to answer your question and to answer the need that you evoked. I guess that, as I mentioned, there's to reach this objective, there is still some limitation that needs to be answered. First, requiring a reflexible. If we want, to be in the metaverse to interact freely with our body, with a dysmorphic body that we might have, it might be important to have a reflexible algorithm that will allow any type of tactile stimulation, which so far hasn't been provided by the algorithm, by our algorithm, as we wanted to really have a restrict protocol in which there was exactly a specific stimulation, but it might be important to study different type of stimulation. And again, as we said, it's hard to. There's virtually a unlimited type of body dysmorphism, so we could see that there was already some differences between two different types. It might be, as I said already earlier, it might be important to study a wider range and to see each one how different impact they have, because each dysmorphism are of different nature and cannot be considered just as one single thing. Is more than just dysmorphism.
I see. Thank you very much.
Thank you very much.
All right, we have time for one more question.
Hello. Mark Satkowski, Interactive Media Lab, Dresden. Thank you for the nice talk. I have a question regarding your procedure. You described that participants had to, in the start, mimic the motion of a VR hand. And how is it done for the block? So how could you mimic the movement of different fingers? And then how did this, that they obviously shouldn't be the same for normal fingers and the block, influence your findings that, for example, the self-touch wasn't as good for the block as compared to the other options?
Sorry, can you repeat the second part of the question?
How does this difference in mimicking the motion influence your results in the end?
Or the motion?
Yeah, this mimicking in the first part of your study.
Oh, so the motion, actually the reason that, so thank you very much for your question. So in this study, the motion, we wanted to include the motion because, as I tried to present it in the start of the presentation, we wanted to try to reflect on what could be actually used during a real utilization, to wider range utilization. And in most of VR, what we saw that was that in most of VR applications, we want to have this visual motor provided, the movement provided. And that's why we wanted to provide in all these cases a visual motor beforehand, before the tactile stimulation, a visual motor stimulation and experiencing actually controlling the body. And I guess you also asked for the block appearance condition. So in the block appearance condition, so as you notice, there is no fingers to the block. So we replaced the movement of the fingers by the movement of a waving movement, because we saw that it needed to be replaced, but it could be replaced by the exact same movement. So yes, that's how we did it.
All right, I know that there were a couple other questions, but for the sake of time, we're going to move on. I'm sure he will be available afterwards for more questions. So let's thank the presenter one last time. All right, the final talk today is titled Studying the Effects of Network Latency on Audio-Visual Perception During an AR Musical Task, and it will be presented by Ellen Dube.
I'm not sure I should say good morning or good afternoon or good evening. I just flew here from Boulder, Colorado yesterday. So if I'm falling asleep because it's like 1 a.m., my body clock right now. Okay, I'm from University of Colorado at Boulder. So if you look at the US map in the middle, that's Colorado. And we are hiring. We're hiring a tenure track professor and also teaching track. So talk to me if you are looking for a job. Okay. So today I'm going to talk about the study of the effect of network latency on audio-visual perception during an AR, augmented reality music task. The rest of my team are Torren, Suibi, Rishi, Emma, Amy, and Mark. And they're not here because we have music performance on Saturday. Okay, so let me walk you through our journey. So I would quickly, in 10 minutes, talk to you about motivation and related work, research questions, and methods, and have a little result and discussion. Motivation. Okay. Motivation is, I'm a drummer, Tony the drummer. So imagine right now we are having a drum circle, okay? I can see you can see me. We are drumming, we can hear each other. Let's think about we're doing this in virtual environment. So we have a project called AR Drum Circle. So when we are doing a virtual environment, it's a spatial thing, right? And we can see you, we can hear you, even just like a little bit. When we are looking at the video of the speaker, we can already sense the delay of the video when people are talking. So this is the spatial experience is tightly integrated. So I can see you can see me, but if I slow down to a certain point, you're going to find it intolerable. Okay, so of course, there are many music collaboration, and we want to be in the moment and in time, right? So most often, we prioritize the audio so you can at least hear the music. So we have many different commercial products like the Jam Kazoo, Jack Trip, and quite often the video is the secondary part, like you just want to hear the music, right? But the fun part, like I said, drum circle. I need to see you, you see me, and we are having a good time. And the atmosphere, we can sense the stuff going around, whether we are having a trance or not. Okay, so we are doing the augmented reality. And what we have here is the Unreal VR glasses, AR glasses, you can see through. And the idea is that, what if we represent you as an avatar, as a drummer, you could be from the other side of the globe. We can see you. How much can we delay the latency? We can figure out the latency that you still can enjoy it, but not being bothered. Okay, so the question about latency between audio and the video still exists. Okay, so the question is, by providing a more immersive visual experience, can musicians tolerate a higher level of the audio-video latency? So there are many related works. So for example, as I mentioned, Jack Trip, Jam Kazoo. So people start to noticing when it's 20 milliseconds, then you start feeling like, oh, something wrong. You don't quite get it, okay? They're dedicated, but look at when we talk about voice, right? So most the threshold for the verbal communication is about 200 milliseconds, and they are remote collaboration. So let's say we are trying to work on things. I'm doing gesture, and if my gesture and my speech is not sync, I think you can still understand what I'm trying to do. But if we're doing like virtual collaboration, trying to do things together, or doing virtual operations, so the latency is becoming an issue. So there are many work that have trying to look at different things. And there are lots of XR, mixed reality, music collaboration. So you can look at the project, desktop VR performance, or share music experience, and or the group singing stuff. So most of them, when they talk about the collaboration, they are not focusing on the latency. Okay. So this is where we come in. Oh, here's another one. So people use VR to study about the sensory perception. Okay. So here's the research question. Network music performance requires very low latency, right? But may not be possible at all times. So it depends on our bandwidth, sometimes maybe with the compression. So how much can we delay the video? And the AR, augmented reality, can potentially give you significant benefit to remote collaboration. So if I can see you, I'm bringing your avatar to my living room so I can see you. So as I can see you moving, even though you were slowing, there's a latency between what I hear and what I saw your hands doing, I probably can tolerate that. The interesting thing is our human mind and our brain is capable of integrating, like we look at the video delay, we can still make sense of that. Okay, so our study is if we are collaborating with a remote partner through the augmented reality, like I said, bring you to my living room so we can drum together. So what is the minimum noticeable delay, the threshold about the network latency? And then how does musician focusing on their attention when they are trying to collaborate in this audio-visual AR task? Okay, so the methods we have, the scenario is that we are collaborating with a remote partner. So we're not bringing all of you, just bring one person. And through the VR, the AR glasses, this one we have Unreal. So we have the avatar in front, and we'll do two different tasks. One is I'm doing the rhythm, maybe boom, 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 boom. You try to imitate me, so you trying to follow me, you know my rhythm. The other one is improvisation. So maybe when I do boom, 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 you're doing boom, boom, okay? So I'm just making things up, like different people may decide to do different things. And then the question we have, so here's Torren. We have the motion tracking bodysuit. So as he was playing, we are recording that, and we use that to drive the avatar. So the audio recorded through from the drum and then to the Ableton. Okay, so the experiment is that you can see here a real person right here, and that's the avatar that's translated in AR. So participants, they can see the AR partner in front of them through the Unreal glasses, and then the drum audio is coming through the MIDI drum and through the Ableton. Okay, so this is what we found, right? So we're doing the same place, so we can adjust the delay, right? Whether it's 20 milliseconds, 40, 60, like all the way to 1200 milliseconds. And so the aim is that we want to collect the information to see when people start noticing, say, wait, okay, not quite there, right? So collect the data. The prior research talk about 50 to 70 milliseconds that people start sensing it. And then if you are, the speech, we can tolerate up to like 150 to 300 milliseconds. All right, so here's the experiment. We invited 24 participants and trying to mimic. So like I said, do the same thing, or improvise. And so with eight different latency conditions, the 20 millisecond all the way to 320. And so then after each task, we ask them the question, how much delay between the animation of the avatar and the audio you hear? Do you feel like there's no delay? Do you feel like, oh, a lot of delay? Okay. Or how tolerable was that? You think this is okay? Or you think, wait, this is a little bit bothersome? Okay. So, and then we asked another question. Did you focus more on the sound? You can hear it. There's no delay. Or on the video? All right. So here's the video. We don't have sound. Okay. But you can see that's an avatar, and you're playing with it. So sequence A is that maybe I play something, and the avatar plays something, and I'm following. And the sequence B is trying to do the improvisation. So you recognize that. So this is the result. So result is that we started to see the difference started showing up around like 160, okay? So we have one result is the mimic, following the same thing. The other one is the improvise. Okay, so the delay tolerance, so you can see between 0, 20, 40, 80, 160. So you can see around 160 people starting noticing that, say, oh, okay, it's bothering me. And the interesting thing is that you can see the improvisation seems to be different. So some of the observations, so we ask people like, oh, so what's going on? The audio-video focus, maybe people are shifting. Sometimes if you say imitations, you are looking at it, listening to it, you follow it. But improvisation, that may be different things, right? So some of the people said like, oh, I was focusing on equal proportion when there is no delay, right? Or improvisation, they say, oh, I'm trying to improvise. So I would listen first, and then I look. So I think because they do listen and look, so then the delay seems to be less noticeable, but still pretty close. Anyhow, so discussion. So you can see the findings, like the previous work. We're realizing that the delay between 160 milliseconds to 320, people start noticing that. And during the improvisation part, people did not experience as much delay, maybe because they listen and they play, right? So they're spending time trying to improvise. And so maybe due to the cognitive load, so there could be a different perception since we asked them the questions. And for the future, we hope to do more precise tests to understand how the audio-video focus people are shifting, and maybe recording their gaze. Do they look at each other, look at their hand? Or what the external application might be, right? So maybe there will be longer tests, so we just do this like few seconds. What if we're having a really jamming for a long time? Okay, and I want to show you, yes, the implication is that maybe we could develop multi-network, so what kind of delay and network latency we can tolerate. And then the other part is that more than just the network infrastructure. What if like this immersive or half immersive augmented reality can give you the illusion? What are the other techniques that you can do so people can still enjoy it and they can adjust the latency and make it enjoyable? I think that's a key word. Okay. So this is the talk, but I want to show you. Yes, okay. Here is the project we're working on called the AR Drum Circle. Can we have sound? We don't have sound. Oh, mute sync first? Okay. No sound.
Use augmented reality glasses to place personalized musician avatars and jam with them. No one to jam with? Create a new avatar and record a looping beat for them to play. Once a new avatar is there, they will play the beats along with you. Now you can jam with different versions of yourself and create compositions on the fly. But hey, wouldn't it be cooler if you could also jam with your friends around the country and around the world? Just like the avatars you make for yourself, your friends appear in your AR headset as avatar musicians. You can now jam with your friends in spatial surround sound. Not sure how to play the drum beat? Color-coordinated splashes show you what has just been played and can help you follow along to the beat. The remote audio still suffers from network delays, but the visual effects work to counteract latency, enabling you to have an AR drum circle in your home.
Okay, thank you.
All right, that was very interesting. Thank you very much. I believe we have a question up here. We have time for 1 or 2 quick questions.
Hi, thank you. Very interesting demo, very interesting work. So going back to the work, I have 2 quick questions. The first one is, did you measure any behavior data or just questionnaires for the?
So behavior data, you mean how people move and that kind of thing. So we recorded some of them, but we haven't really analyzing.
And in terms of the actually in both tasks, are they sequential or synchronized? So for the mimic, do I try to do what exactly the avatar do at the same time, or do I let them do it first and then try to copy?
Trying to do, well, the first time you probably hear it and then you mimic, right? So you can try to do it at the same time. If they do, don't.
I see. So they start and I try to join in.
Right.
Get it.
So they join, they can try to be synchronized, right? And the second part improvise is that you hear it, but then I'm trying to cut it in.
Yeah.
Yes.
And then my second question is, your work is probably focused on, trying to get audio first and then see the delay this way. That makes sense. But I wonder from a theoretical perspective, how about the other way? If I have visual first and audio afterwards, do you think the tolerance will be bigger or smaller? Just some insights on that. Do you have any?
I'm not sure I have the insight, but one of the things is that, for example, if we're using Jack Tree, most of the time just the audio, you have no video. If we're using Zoom, most of the time we have video, but the audio was really delayed, and that was intolerable because I think they're also trying to silence some of the background noise, and they could not tell which part is music, which part is noise.
I see. Interesting.
Yeah.
Thank you.
Thank you.
We have time for 1 more question.
Okay.
Over there.
Sure.
Hello, Tiffany Long from ETH Zurich. Very cool presentation, thank you. I was wondering if you observed any influence of the latency on the tempo or on the complexity of the music output. Anything regarding that?
We try to keep it simple, and then we started doing the experiment because originally when we were doing things, we recognize they are delayed, and we realized that people are jamming at it and we're having fun, but that was not a pattern they have originated. And we found that fascinating. So I think we do the control experiment because we wanted to know how much people can tell the difference. But I won't have data to say how much the simple or complex things will be. So that could be future work. Thank you.
Okay, thank you.
All right, let's thank the presenter one last time.
Thank you.
And that concludes this session. Thank you all for joining. As a quick reminder, we are now doing a small tea break. There is currently a sponsor workshop with Enovim, so if you find that interesting, go look at that. On your break, please do check out the posters. There's a lot of very interesting ones. In this room, the next session will be tracking registration and reconstruction, and across the barrier from us will be sensation and perception. Thank you again. Have a good day.
Hey, we're Zoom. You probably
Hello, I'm Fernando Reyes Avilés at Graz University of Technology. And today I'm presenting our most recent work, Compact World Anchors, registration using parametric primitives as in description. Nowadays, many modern devices ship powerful depth sensors, for example, the iPad Pro with the LiDAR sensor. And such sensors can be used for scene understanding or plane detection, for example, which allows AR applications to enable compelling interactions between the virtual objects and the real world. Also, AR applications rely on a reference that persists over time to localize within known environments, leveraging these surface detection and scene understanding capabilities. For example, Azure and AR Anchors and AR Foundation are two examples of popular technologies which were recently introduced with such capabilities. These anchors are usually used to create, to create a reference, and they are created using natural features and that information. A downside of these anchors are that they need a Wi-Fi connection and some cloud services which requires the users to have some sort of subscription to some cloud service. So we thought on leveraging these high-level information from the surface detection and plane detection of these new devices to enable AR applications in indoors environments. We specifically thought on leveraging, for example, parametric primitives like, for instance, planes, cylinders, or spheres. And we introduced two main new concepts, compact scene representation and a parametric primitive-based registration method. The compact scene representation encodes the known environment into a unique description of the scene, which allows or serves as our anchor to relocalize. And the registration method that we propose takes as input the parametric primitives compared, for example, to individual points from point clouds or corner or edge-based detection algorithms. So let me tell you first about the registration method we use to find the 6 degrees of freedom transformation to register the model to the scene content. For example, here in this picture, we have two sets of planes in two different coordinate systems, some planes in the model and some planes we observe in the scene in the live mode. So what we can do from, for example, the planes in our database is to compute a set of lines and points where these planes intersect. So as long as these, for example, in this example, the planes are not in some degenerate configuration, we can always find the intersections of such planes and also this point where all the planes intersect. We can also do the same for the primitives in the scene that we are observing, and assuming we know the correspondences of the model to scene sets of data, we can always find the transformation between these two sets, between these two coordinate systems. With 3 lines and 1 point, we have enough information to build a linear equation system to find the rotation matrix in 9 unknowns and the translation in 3 unknowns. So we talk about the registration, but we need to find the correspondences first in order to be able to extract such lines and such points from both sets of data. So what we use to find the correspondences is our concept that we are introducing, the compact world anchors. And to build such anchors, we are using an algorithm called point pair features. So the point pair features are built using pairs of oriented points. This means that each point also has a normal associated to it. And what we do is we find the angles between the normals of such oriented points and also the normals between a vector D which connects such oriented points. With these angles, we can build a 3-vector feature, which is robust enough from our test in order to create a unique description of a known environment. We do this for each and every point in the scene, and we store all those 3-vector features in our compact anchor. Let me give you a glimpse of how these anchors look like. So on the left side, I have a compact anchor, which is stored into a JSON file. In the blue boxes, I am highlighting the unique identifiers of the primitives used to build the 3-vector feature. And inside the red box, I have the 3 angles I showed in the previous slide. We do this, as I said, for each and every pair of primitives in our scene, and that's all our compact anchor contains. On the right side, I have an example of a parametric model. And in the black box, for example, I have the parametric equation of a plane consisting of the 4 parameters. And in the blue and in the yellow box, I have the 3D coordinates of all the points which define the boundary of such plane. With this, I want to show this very minimal and lightweight information we use to find the correspondences and to register the model and the scene content. So in order to find the correspondences, what we do is we compare the already offline computed features that we have in our database to the online computed features from the parametric primitives we observe in the scene. So we first measure the similarity between these 2 sets of features, and all those features which are smaller than some certain threshold give us some correspondences. Here I am trying to encode the correspondences with colors. So for example, here the orange plane in the scene would correspond to the orange plane in the model. Because the scene may be a bit symmetric or for some noise in the scene, we may get wrong correspondences. Like here, I am trying to show. We have the blue plane being corresponded to the green plane in the model. And what we do to avoid such mistakes is to also use a voting scheme, and only those correspondences which receive some certain level of votes are accepted as true correspondences. The first test we did was using Infinitam to reconstruct a small room. And here in the picture, I have on the right side, on the left side, sorry, the reconstruction. And on the right side, I have the parametric model we created using a structural modeling algorithm. In this model, we have 45 parametric primitives, including cylinders and planes, from which we could extract approximately 400 3-vector features, which we stored in our JSON compact anchor. We also created an Azure compact anchor with a HoloLens device of the same space, which approximately used 4.6 megabytes of space in our disk. And in comparison, our compact anchor uses only 20 kilobytes of space. We also tested our registration and scene description with some commercial SLAM that you all have access to. We implemented this in an iPad Pro using Unity and AR Foundation. So AR Foundation gives us the possibilities to detect planes in the scene, which in this short clip are the yellow planes in the video. And we have 2 modes in the application we implemented, the recording mode and the live mode. During the recording mode, the user can scan the scene to find some planes and put virtual objects, in this case the avatars, on the desk in any position and orientation the user wants. We save the planes with their parametric equation, the bounding box, and also the positions and the orientations of the virtual objects in the model. This is all stored in our compact anchor, and we later, in live mode, we can come again with the database we have already, scan again the scene, and quickly relocalize within this known environment. As we can see in this short clip, the avatars were positioned in the same orientations and the positions where we created the model. And we only need a few primitives in order to be able to relocalize. So our contributions were a new compact scene representation, which encodes a known environment in a very lightweight fashion, and also a new registration method which takes as input high-level information like parametric primitives instead of, for example, individual points. We also demonstrate how our approach works in real use cases. And for our future work, we would like to implement and demonstrate that the lightweight nature of our anchors enable us to create cross-platform applications with, for example, different devices like the HoloLens and the iPad. And we also would like to explore the possibility to increase the robustness of the feature in order to be able to not only find the correspondences in a small database, but rather in a very large database where we can carefully select the scene where we are in. Thank you for your attention, and my name is Fernando.
Thank you very much. Okay, so let's move to the QA time. So are there any questions?
Hey, good talk. So I guess one of the key questions which I have is, how well does it work, or does it work on dynamic obstacles at all, or dynamic objects at all?
No, this is thought to be used in scenes that do not change at all. For example, it would not work in a scene like this where you can easily move the chairs, for example, around here. It is more thought to be used in environments where the furniture or the structure of the environment will not change over time at all.
Okay, so this is only for static objects.
Yes.
And my second question is, how complex objects can this method do? Like in terms of structure, shape, or whatever?
Yeah, right now, for example, the AI Foundation or the scene understanding on the HoloLens is only capable of detecting planes, planar surfaces.
Yeah.
But our algorithm works with any kind of primitives that your SLAM system or your structural modeling algorithm could detect. So we are independent of the SLAM platform. And we have only tested so far with plane cylinders and spheres. But in theory, it can be extended as long as your SLAM or your structural algorithm is capable of detecting complex objects. We are not on the, for example, object detection like SLAM++ level. We are rather on the more primitive-based world.
But I guess, can you break down an object into more simpler primitives and then like cylinders and cubes?
No, we are not able to. We didn't explore that, so that has to be provided to our solution. The primitives should already be provided to us to be able to create the compact anchor and the registration.
All right, so like, it won't be able to decompose objects into simpler primitives?
No, we didn't work on this.
Okay, okay. All right. Okay. Yeah, good work, thank you.
Thank you.
Thank you. So if you have any short questions, okay. So thank you very much.
Thank you.
So let's move to the second presentation. This presentation will be held in person. OSLAM, Reversing Object for Camera Localization in Visual SLAM. Sorry. This is ISMAR conference paper and given by Matthew Zins, Jill Simon, Marie Odile Berger.
Okay. So hello everyone, I'm Mathieu from INRIA, and I will present our work called OASLAM for Object-Aided SLAM, in which we leverage objects to improve relocalization of visual SLAM. So recently, many works have used semantic information to improve localization. And in particular, objects are very interesting because they can be detected in a very robust way thanks to the advances of deep learning. So for example, with YOLO or faster RCNN. So in this work, we model our objects with ellipsoids in 3D and with ellipses in the image. And also, we use previous works which propose solutions to compute the camera pose from ellipsoid pairs. So we had two main objectives. The first one was to build an automatic system for object mapping. And then we want to use this object to improve the relocalization of a visual slab. So this is the global architecture of our system. It takes as input RGB image, no depth, and object detections that are provided by YOLO, for example. The architecture is based on OrbSlam 2, and we added the elements that are in blue. So I will first describe the object tracking part. So we adopted several strategies for the object tracking. The first one is a short-term strategy, which uses only 2D information. And it's possible because usually the camera motion is small between two frames. So it's based on IOU between boxes, and it's constrained by categories. But this strategy was not sufficient when the object gets out of the image and back again in the image. So that's why we also used a long-term strategy, which is possible once the object has been estimated in 3D. So once we have the ellipsoid, we can project it into the current frame. And again, the association is obtained using the intersection over union with the detections in the image. And these associations are also constrained by the object categories. So to find the optimal association, we used the Hungarian algorithm. And this tracking was very interesting for small or textureless objects because it relies only on the geometry of the object. However, it can be affected by truncated detections. So that's why we also used points to establish association and to track objects. So our system maintains association between 3D landmarks and the 3D ellipsoids. And then when we have a new frame, a new detection, we count the number of 2D key points that are inside the box and which are associated to a certain object. If this number is sufficient, we also consider the association. So this strategy was more efficient for textured objects, and also it handles well the truncated detections. So now I will go to the object mapping part. So the idea was to reconstruct the object as soon as possible so that we can use the reconstruction to help the tracking. So there exists an analytical solution to reconstruct an ellipsoid from 3 ellipses. However, we found that in practice it was relatively unstable in our case because we want to reconstruct for relatively close viewpoints. So that's why we used a different strategy, which is simple but reliable. And we want to first reconstruct the object as a sphere. So we triangulate its center, and we compute its radius as a sort of mean of the box sizes. And then we refine this sphere as an ellipsoid by minimizing a reprojection error, which is the Wasserstein distance between the projection ellipses and the detection boxes. Then, before inserting the object in the map, we first check that its reconstruction is coherent with all its detections. So again, it's based on IOU. And if the test passes, then we insert the object in the map. And once the object is in the map, it's continuously refined by new observations in keyframes. Again, we minimize the Wasserstein distance, so between the projections and the detections. And this optimization can be relatively slow, so it's executed in parallel in a separate thread. Now I will describe the relocalization. So this relocalization is used when the system is completely lost. For example, if the camera was occluded for some time, the system needs to relocalize from just the current image and the map that was built so far. So traditionally, OrbSlam 2 first search keyframes candidate in the past trajectory based on appearance, and then it tries to find point matching, but it's a difficult task. And we propose that when this is not possible, when it fails, we compute the pose based on object detections and the object in the scene. So for that, we use a previous work, which can compute the pose from 3 object detections, at least 3. And we use this rough estimate of the pose to guide the 2D, 3D point matching. And finally, we compute a more precise pose using the point associations. So now I will show you some mapping results. So in the video, you have on the right the frames, the RGB frames with the detected and tracked objects. And on the left, you have the reconstructed map with the points, the ellipsoids, and also the estimated camera trajectory. So this video was recorded in real time. So this is the running time of our system. And you can see the ellipsoids that are a bit moving because, as I said, they are continuously refined by all the new detections. Now the video is accelerated. So another result on another scene. Here we compare our system with the EAO SLAM, which is another object-based SLAM, which reconstructs objects either with ellipsoids or with cuboids, depending on the type of the object. And if you compare both maps, you can see that the green ellipsoids in their map are too large for the object. They correspond to a bottle and to a cup. And also you can see that the mouse and the book are duplicated in their map. They appear both as ellipsoids and cuboids. On the contrary, in our map, the ellipsoids are more fitted to the objects. And also EAO SLAM requires to know the vertical of the scene, which is not the case in our system. Now I will show you some relocalization results. So again, on the desk scene, here we split the sequence into two parts, 700 frames for the mapping. So you see the orange trajectory at the top right. These frames were used to map the scene, and then we use all the other viewpoints to relocalize. Here we evaluate relocalization, so we force relocalization on each frame independently. You can see the red trajectory is the ground truth, and in blue you have the results of OrbSLAM2. You can see that it's accurate, but it only works for viewpoints that are close to the mapping viewpoints. In our case, so the green ones, we are also relatively accurate near the mapping viewpoints, but we can provide a relatively good pose also for other viewpoints. Another results on a custom scene, again, we did the mapping from mostly one side of the scene, and then we changed the camera height, the orientation, we did the complete tour around the scene, and also its distance from the scene, so the zooming. And again, you can see that OrbSLAM2 is limited to viewpoints that are similar to those used for mapping, whereas our method, which uses object endpoints, can also estimate the pose from much larger viewpoints. So now I will show you an example of relocalization used in a SLAM. So you will see a video. In the first part, we map the scene mostly from one side. Then we force the system to get lost. And then we look again at the scene from another viewpoint, and the system should relocalize, and the mapping should continue. So at the top, you have OASLAM, our system, and at the bottom, OrbSLAM2. So this is the mapping part. You can see that we reconstruct objects, and OrbSLAM2 only points. Now, both systems are lost. And when I look again at the scene, our system can relocalize and continue the mapping, whereas OrbSLAM2 is still lost. Another example, this time we want to initialize camera tracking from a pre-built map. So for example, if one user has mapped a scene and added some virtual elements inside, and another user wants to initialize tracking with respect to this map, but from a different viewpoint. So again, the relocalization is used. So at the top, again, it's OASLAM, our system, and at the bottom, it's OrbSLAM2. I displayed the ellipsoid on both, just to indicate if the estimated pose is good or not, even if OrbSLAM2 doesn't use objects. So you can see that our system could relocalize very quickly, and Orchlam 2 is still lost, and now it's good. So it really needed viewpoints that were similar to those used for the mapping. So to conclude, we built an automatic object mapping system, and then we used this object to improve the relocalization of visual SLAM. In particular, we make them collaborate with points to bring their respective benefits to the precision of points and the robustness of objects. And in the future, we would like to use objects also for loop closure detections. And we would like to extend our experiments to larger scale, because in our experiment, for now, we tested in a scene of the size of a room, but large scale will induce other challenge like high combinatorics and probably also ambiguities. So, thank you.
Thank you very much. So do you have any questions? Okay. Actually, I have a question. I'm curious about how do you detect the object in the video, and what kind of primitive for describing the shape of the detected region?
Okay. So here I use YOLO to the object detector, but actually you can use any detector that you want. Either you can use a pre-trained version if it's general objects that are known by, that are present in the COCO dataset, or you can also fine-tune on your objects. And the primitives, so we use only ellipsoids in 3D, and in the image we detect the object with boxes, and then we take the inscribed ellipse to get an ellipse of the object.
Okay, thank you very much. So, are there any questions? Okay. Okay, thank you very much. So we are going to move to the third presentation. This presentation is online. Box fusion, dense tracking and mapping with voxel-based neural implicit representation. This is an ISMAR conference paper given by Xiaoli Yang, Hao Li, Hongjia Tsai, Yuhan Min, Yinxin Liu, Gyofan Chang. Video.
A dense SLAM system combines voxel-based representation with neural implicit fields. In traditional dense SLAM systems, such as Connect Fusion, they often divide the scene into small elements called voxels. These voxels contain scene information, for example signed distance values, normals, etc. More sophisticated methods use hash structures to accelerate voxel insertion and lookups. Inspired by NeRF, neural implicit surfaces can obtain continuous scene attributes such as SDF and color by querying the network using position and viewing direction. Our work is inspired and constructed from these previous works. In comparison to traditional methods, one would find the benefit of neural implicit surface quite appealing. For example, 1. With only a few parameters we can represent large-scale continuous scene maps. 2. The continuous property allows the network to fill in missing data, such as missing depth values. 3. We can arbitrarily interpolate the network to obtain different granularity of the said properties. However, the neural implicit surface still has some problems that affect its practicality. For example, 1. It uses a single neural network to store all potential scenes, making the scene difficult to segment. 2. Requires prior knowledge of potential scenes, not applicable to unknown scenarios. 3. The speed is slow, limited by the network representation ability. Our method combines the advantages of neural implicit methods and traditional TSDF methods. Specifically, our scene is divided into appropriately sized voxel blocks, where each voxel contains feature embeddings that can be extracted by the neural network to present SDF and colors. Our method reconstructs only visible surfaces, which significantly reduces the amount of memory required and increases processing speed. The key to our system is the voxel-based volumetric rendering method. For each camera ray, we first identify voxels that would be hit by the ray. Then we sample points inside the voxels using a fixed step ratio. These points are fed into the neural decoder to obtain signed distance value and color. We take a sequence of ordered RGBD frames as input. The tracking process consists of a pose update step where the initial pose estimate T0 is iteratively updated to minimize a combined loss of images, depths and SDF constraints. The same method is used for mapping as well, except that we also update the map parameters as well as the key frame poses. The feature embeddings inside the voxels and neural implicit network are shared between the mapping and tracking processes. We seek to accelerate this method by introducing multi-level octree and local latent embeddings. We use Morton coding and octree to efficiently manage voxels. Morton coding, also known as Z-curve, allows us to efficiently traverse the octree with minimum effort. Given a Morton code, it is also possible to find its neighbors in a single step. Unlike existing methods which pre-allocate the potential reconstruction space, our Vox fusion system can gradually create the voxel grids and expanding the scene. Thus makes our method more practical. Here we show a demo of our system running on a single GPU. For better visualization, we accelerate the demo by 20 folds. Our method displayed better results compared to the current state-of-the-art systems. As can be seen from the results, we outperform both ISMAR and IMAP. Our system also shows better reconstruction of small details. Here we show an example reconstructions from the replica dataset. These results show signed distance-based representation handles thin structures much better. We directly apply our method to lidar scans from an iPhone 13 Pro. As shown in the slides, our method handles outdoor scene equally well. Quantitatively, we also surpass competitor methods with a large margin, especially in terms of tracking accuracy. We also compare reconstruction qualitatively. We use the metrics from ISMAR, namely accuracy, completion and completion ratio. Unsurprisingly, better pose estimation leads to better reconstruction. Our scene is much more accurate and complete when compared to other methods. We show the average time spent on important components for each iteration. Depending on the scene complexity, our method can take around 150 to 200 milliseconds to track a new frame and 450 to 550 milliseconds for the joint frame and map optimization. Our system can be applied to AR applications with minimum modification. We show here an example of randomly placing objects inside the virtual scene. Thanks for watching. Please feel free to ask any question during Q&A.
Thank you very much. So let's move to the Q&A time. Are there any questions from the audience? Okay, so can I ask a question?
Okay.
Okay. I'm interested in the training set for your voxel-based neural representation. What kind of data set do you use for training?
We don't use any training set. It's a scene-specific, just like normal SLAM system, you can run in arbitrary field without training.
Okay, I see. And you are applying your method to the static scene right now. So when you are going to apply the method to the dynamic scene, what kind of problem will be happen?
Our method is capable of removes dynamic scene during reconstruction by thresholding some the loss such as depth loss or color loss, but we cannot modeling the dynamic scene yet. But our future work is trying to modeling the dynamic scene as well during the reconstruction.
I see. So right now you are ignoring the dynamic object in the video.
Yes.
Okay,
Yes.
I see. Do you have any other questions? Okay. Okay, so thank you very much for your good presentation.
Thank you.
So next is in-person presentation. That is the integrated design of augmented reality spaces using virtual environments. This is ISMAR conference paper given by Tim Shukargil, Yin Chen, Nathan Marzen, Martia Kortova. So please start if you're ready.
Thank you. Hi, everyone. My name is Tim Scargill. I'm a PhD student at Duke University, and today I'm presenting our paper, Integrated Design of Augmented Reality Spaces Using Virtual Environments. So markerless AR provides us with great convenience and flexibility in that we no longer require predefined images or markers to position virtual content. Instead, we can rely on device pose tracking results available through visual inertial simultaneous localization and mapping, or VI-SLAM. However, this still imposes a requirement for natural features, i.e. visible textures in the surrounding environment. And this requirement naturally comes into conflict with human preferences for minimalism in architecture and interior design, which frequently result in built environments like the meeting room in the bottom right here. So the question is, how do we manage this conflict? How do we design environments that work for both AR systems and human occupants? In order to address these diverse factors in the design process, we propose the adoption of integrated design practices. This is an established approach in modern building design in which a wide range of conflicting requirements are considered, from cost and sustainability to aesthetics and energy efficiency. In this work, we develop an integrated design methodology for the real-world environments that host AR experiences that brings together both system and human factors. We focus here on device pose tracking and user comfort, but our approach is extendable to other factors that affect the quality of AR experiences, such as eye tracking performance and virtual content visibility. So taking first pose tracking, performance, VI-SLAM performance is traditionally evaluated using benchmarks such as TUM-VI or SenseTime datasets. And these are extremely valuable tools, but because of the logistics associated with the setup and calibration of an optical tracking system, like OptiTrack in our lab in the top right there, which is required to capture accurate ground truth pose, they're limited to a small number of environments, such as the lab setting in the bottom here, not representative of the diverse environments in which AR is designed to be used. This limitation, along with the challenges associated with systematic adjustment of real environment properties, leads us to the use of virtual environments for tracking evaluations. Another key advantage of virtual environments is that they can be reused to study human factors without users having to be physically present in an environment. Our vision is that just as crowdsourced remote testing is available for websites and software, we can employ this for AR environments. So the contributions of our paper are as follows. We developed the first VI-SLAM evaluation method that combines the range and flexibility of virtual environments with the complexity of real rather than simulated inertial data. We performed the first systematic quantitative experiments on the impact of visual texture on VI-SLAM performance, providing insights on how the level of edge strength and complexity in a visual environment affect tracking accuracy and robustness. Finally, we then conduct a case study of our integrated design methodology in a real-world scenario, AR museum design, combining the aforementioned VI-SLAM evaluation method with VR-based evaluations of user satisfaction. So, in our VI-SLAM evaluation methodology, which is illustrated here, we create a virtual environment in a game engine such as Unity or Unreal. We use a custom script to generate new visual data, i.e. the camera images, in that virtual environment from the ground truth pose in the existing SLAM dataset. We then combine that new visual data with the original inertial data from the dataset and run it through an open source VI-SLAM algorithm such as OrbSLAM 3. We analyze tracking performance, including correlations with visual and inertial input data properties, by extending an existing trajectory evaluation tool and developing our own custom scripts. The code required for implementation of this methodology, which we term virtual inertial SLAM, is publicly available on GitHub. So on this slide, you can see our implementation, virtual inertial SLAM. On the left, we have 2 examples of realistic virtual environments created in Unity's high-definition rendering pipeline. And by implementing our methodology, we can then run the trajectory from an existing data set, in this case sense time, in one of these virtual environments. You can see it running in OrbSLAM 3 on the right here. And note that the high-definition rendering pipeline not only allows us to reproduce high-resolution textures, but it also reproduces accurate lighting effects, such as the reflections of the 3 ceiling lights moving on the marble floor there. So next, we used our methodology to examine the impact of visual texture on tracking performance. We quantified the properties of visual texture using edge strength, measured using the variance of the Laplacian, and complexity, measured using Shannon entropy. We tested 3 sets of visual textures: basic textures, which are binary images which allow for varied edge strength with very limited complexity; complex textures covering an even distribution of edge strength values with varied complexity; and realistic textures, such as stone, wood, and wallpaper designs, which are more likely to be employed in real-world scenarios by designers. Given that these are the first quantitative experiments on visual texture, we first examined their effect in isolation without natural 3D objects by applying the textures to the walls, floor, and ceiling of a 6 by 6 by 4 meter room in Unity. For each texture, we conducted 100 trials with OrbSLAM 3, covering 10 different lighting levels for each of 4 different SLAM trajectories: TUM-VI Room 5, and Sense Time A1, A4, and A6. For the full results of our visual texture experiments, I'll refer you to our paper, but I'll provide a sample of them here. Our VI SLAM performance metrics were post-estimate relative error, with the results for the 100 trials displayed in the box plot here, and robustness, which is the mean percentage of tracked frames across the 100 trials, displayed in the line graph. Overall, we found that the impact of visual texture was greatest in the more dynamic trajectories, such as TUM-VI Room 5. On the left, we have the results for this trajectory with our complex textures. In general, the relative error decreased with increasing edge strength, as expected, but we can see that complexity also played a key role. The texture with the lowest complexity, C8, the black and white texture there on the left, resulted in much larger relative error than textures with comparable edge strength. On the right, we have the results for our realistic textures. 3 out of 4 of those realistic textures with high edge strength, stone R7, the plant wallpaper R8, and brick R9, perform much better than the other textures with low edge strength. The exception to this was R10, the marble texture, the fine marble texture. This one was, because it's a fine texture, was much more affected by motion blur in the camera images, resulting in lower robustness and higher relative error. Moving on now to the evaluation of human factors in our integrated design methodology. As previously mentioned, we can reuse the virtual environments we created for our tracking evaluations in VR-based occupant satisfaction studies, guided by existing studies in environmental psychology. So we build these virtual environments into a VR application in which a human participant can freely explore or perform tasks related to that environment. And we use survey software for self-reporting of comfort and satisfaction during those experiences, and analyze our results using custom Python scripts. Using the VR headset, we're also able to capture a variety of other data, including head pose, eye movements, and physiological signals, such as heart rate. And in ongoing work, we're implementing motion and cognitive attribute analysis from these data. Bringing together our evaluation of tracking and human factors, we then conducted our case study of our integrated design methodology for a real-world scenario, AR museum design. With growing demand for AR experiences in museums and art galleries, our work extends a body of existing literature on how museum environments affect visitor satisfaction to include the support of markerless AR applications through VI SLAM. In order to obtain an authentic perspective on museum design factors and potential challenges associated with incorporating AR experiences, We collaborated with a subject matter expert, the head of exhibition design at Ackland Art Museum at UNC Chapel Hill. To implement our case study, we created 4 variations of a virtual museum environment containing a small exhibit on ancient Egypt with 3D models of real historical artifacts. Museum A had blank walls and a wooden floor. Museum B had marble walls and a marble floor. Museum C had wooden walls and a marble floor. And Museum D had the Egyptian textured wallpaper with a wooden floor. We conducted VI SLAM evaluations with 10 trials on the 3 sense time trajectories, and we conducted an IRB-approved VR-based user study on occupant satisfaction with 15 participants. As with our visual texture experiments, I'll just provide some sample results here. In our VI SLAM evaluations, the most traditional museum design with the blank walls, Museum A, performed the worst with the highest relative error over 10 trials on sense time A1. Somewhat surprisingly, the marble textures in Museum B outperformed the textured wallpaper in Museum D. And furthermore, when asked to rate on a 7-point Likert scale how easy it was to focus on the museum objects, participants also rated Museum D the lowest, noting that they were distracted by the very textured wallpaper. So, simply by following the qualitative environment requirements provided by AR platforms, designers might easily be tempted to choose Museum D because the qualitative guidelines say, have a textured environment, it'll make your AR experience better. But in fact, our findings clearly contradict this, that it's neither the best for tracking and it's also bad for humans, illustrating the importance of our integrated design methodology. So in conclusion, we've developed an integrated design methodology for AR environments that considers both tracking and human factors. We developed the first VI SLAM evaluation method that combines virtual environments with real inertial data. We performed the first systematic quantitative experiments on the impact of visual texture on VI SLAM performance, and we conducted a case study to demonstrate our integrated design methodology. In future work, we'll examine more realistic virtual environments that contain more natural 3D objects, as well as simulation of AR content in our user studies. We'll investigate the properties of texture that support high-quality tracking while having low perceptual impact on human users, and explore the integration of VI SLAM-based tracking artifacts into our VR simulations. Finally, I'd like to acknowledge the awards which supported this work and point you towards our open source implementation code and examples, which you can access via the link or the QR code on screen here. Thanks for your time, and I'll be happy to answer any questions.
Thank you very much. So, are there any questions from the floor audience?
Yeah, thank you for the amazing presentation. This is Linda from TU Munich. I have the question, I can easily imagine that this would also work for SIF descriptors or other descriptors. What do you think about learned features in the future?
Yeah, absolutely. It's something that I hadn't actually considered, but thank you for the question because now we definitely will consider it. Yeah, I think it could definitely work, and we'll include that in our future work. Thank you.
Hey, good work. Hey. So, I guess that you have tracking issues as well as human factors, right? What is the eventuality? Like, I understand both of them point to different directions, right? It seems like with textures which are with sharper edges, so to speak, are great for tracking, but bad for distractions, right? So what is your, I couldn't figure out what's your suggestion out of these studies? Like,
yeah, essentially is that we can't just judge and decide on the best AR environment design by applying simple rules. We need to apply an integrated design methodology like this that examines both tracking and human factors. And yeah, as I said, our long-term vision is that we do this through crowdsourced, like remote testing of our AR environments, distributing the environments to VR headsets, and then yeah, asking users to rate their experiences in those environments. Long term, I think it would be great to integrate the tracking performance into the user studies, because right now it's still somewhat separate. So I think if we can integrate them more fully, that would be even better. Yeah.
Okay, so and quick second question, if I have 30 seconds. I guess the eventual use case would be an AR application, right? You go to Auckland and then you have a device, you roam around and you have sort of this augmented intelligence on your device, so to speak, right? But your user study was a VR user study, right? So is the user study more to, like, what was the purpose of that user study? Because the tracking would be on AR. The VR would, you would just load the model and then you won't have the tracking issues, right?
Right, yeah, no, thanks for the question. Yeah, so in the museum user study, the VR environment was essentially just simulating the real world environment. So that's simulating like the real objects that a user would find. We didn't actually simulate any AR content in that VR simulation, but that's our next step of like, how do users then interact and feel about how the real environment affects their perception of AR content.
Oh, okay. Well, thank you so much. It's been 8 years since I visited Auckland.
Oh, really?
This is really fun to see newer dimensions of the museum.
Thank you.
Thank you. So if you have any short questions, it's okay. So thank you very much. So next presentation will be online. Casual 6 DOF, free viewpoint panorama using a handheld 360 camera. This is TVCG invited paper and given by Lawson Chen, Fang Du Chang, Simon Finney, Andrew Chalmers, and Tae-Hun Lee. So please start the presentation video.
Hi everyone, my name is Rongshen Chen. I am a PhD student at Computation Media Innovation Center at Victoria University of Wellington. I'm here to present you our TVCG paper, Casual 6DOF, free viewpoint panorama using a handheld 360 camera. The focus of this paper is about solving the problem of novel view sample size. The novel view sample size is to generate a new view at a position outside of its capture location and generate corresponding view for the new location. This is important in many application areas, such as telecollaboration, video conferencing, or general entertaining. Although many works related to it has been done, most of the work were focusing on perspective images. The advantage of perspective images is it's easy to access. However, its limitation is it has very limited field of view. To capture enough data for reconstruct 6DOF, people normally need to capture in more than one direction. The capture process can be very time-consuming as the scale of the capture scene increases. On the other hand, 360 camera is designed to capture surrounding view in a single shot. Thus, compared to perspective camera, using 360 camera has the advantages of easy and faster capturing stage. Since now consumer-level 360 camera are now widely available, the accessibility is no longer a big issue. However, directly using 360 camera in prior works will not work straight away, because 360 images has much wider field of view compared to perspective images, and also the distortion caused by the image stitching. There are some prior works that use 360 panoramic images and view synthesis. 360 RGBD video rendering the 360 panoramic image into a 3-layer mesh and perform imprinting to filling the occluded area. However, the limitations of this method is it's not scalable to large scene. The viewer will only able to perform really small translation around a single capture point. And then there's OmniPhoto. OmniPhoto synthesizes novel view by using optical flow and geometric proxy as guiding information to warp and blending near image together. This method has really good visual quality, and since it's using optical flow, it's also able to address dynamic object within the scene. This method also has a limitation on scalability, so it only works with a small scene. And more importantly, it only enables 5DOF, so it's not really solve the 6DOF problem we aim to address in this paper. If we look away from 360, the prior works on image-based rendering enable large-scale 6DOF but not using 360 panoramic images. Inside out and deep blending are the two most recent methods in this field. This method requires sparse and dense depth as input. The sparse depth can be acquired from motion software such as CoMap, and the dense depth map can be either acquired from KitNet sensor or perform a dense reconstruction. Deep blending achieves dense reconstruction by performing surface reconstruction on the sparse geometry reconstructed by structure from motion. Therefore, the quality of the dense reconstruction is depending on the sparse reconstruction. This would cause issue when we try to use this method on 360 images. Since 360 image has much larger overlap area, it would have much noisier match feature report. This leads to noisier sparse reconstruction result, and thus would cause more issues for surface reconstruction, lower the performance of these methods. Of course, nerve-based method proposed recently also has the capability to generate 6DOF content. However, nerve-based method has limitations on its fidelity. Due to its volumetric nature, the result of nerve-based method will always look foggy and blurry when used to reconstruct large scene. Although recent methods such as block nerve and urban nerve tries to address this issue with approaches such as separating the large scene into small training blocks, or aid the training with depth capture using LiDAR, the result of this method are still not as high fidelity as traditional image-based rendering methods. This is why we decided to approach the 6DOF problem with the more traditional image-based rendering pipeline. The contribution of this paper is as follows. We develop a novel pipeline that naively takes 360 panorama as input and generates 6DOF content. We show how depth can be reconstructed from given 360 images. We demonstrate how we implement our view synthesize method that enables to run in 30 FPS that allows interactive exploring of the capture scene. Here is the overview of our pipeline. Our pipeline has two parts: the offline geometry reconstruction and online view synthesis. As like many other view synthesis methods, the first step of our pipeline is to perform camera registrations to recover the camera pose of the given 360 panorama image set. With the camera pose known, we then estimated sparse depth and dense depth for each input 360 images to avoid the potential surface reconstruction failure caused by noisy sparse depth. We did not use surface reconstruction to recover dense depth as in prior work. Instead, we ran a separate multi-view stereo-based depth estimation to obtain the dense depth. We then use our depth refinement process to further enhance the depth quality by solving the depth inconsistency between views. During depth refinement, we first fuse the estimated sparse depth and dense depth together from an initial depth. We then use ray matching to find out the highest common depth across neighbor views. This will remove any outlier depth that are too close to the camera and improve the depth inconsistency across neighbors. We perform forward depth reprojection to fuse the corrected depth together. This step recovers the depth that accidentally eroded in previous step and improve the depth by maintaining the shape of the object. We then fuse this depth with sparse depth again and apply morphological operation to obtain our refined depth. Here is a visual comparison of how the synthesized images improves alongside the depth refinement. A shows only with the sparse depth. B shows the result of fused sparse depth and dense depth together. C shows the result after depth correction. D shows after forward depth projection. And E is with our final depth. With geometry information recovered, we can now perform view synthesis. We use depth-based image rendering to achieve novel view synthesis. We first form the depth map at the given location by forward projecting the neighboring views. Then we use morphological closing to remove outliers depth and fill in the small gaps between pixels. Finally, we use the same ray matching method to correct the novel depth map to minimize its inconsistencies with the existing depth. With the depth at given location being generated, we can now perform pixel extraction. We blend the extracted pixel together by weighting them with their angles to the target position, the distance between it and the novel position, and its depth correctness. Now, the result of our method. We evaluating our method using three matrices: the peak signal-to-noise ratio, the structural similarity index, and the perceptual similarity. Similar to prior works, we did not evaluating the top and bottom view, since viewers tend to fixate to equator when exploring the panorama. As you can see in the table, our method performs better than previous method in both indoor and outdoor scenes. Similar to other image-based rendering method, the number of 360 panorama given would affect the process time and the quality of normal sample size. In terms of process time, our method took more time than previous method, as we need to run a second depth estimation to estimating the dense depth map. However, since we do not have to store mesh as additional data, we require less storage compared to previous method. Here are the qualitative comparison between our method and previous method on indoor sim. And here are the results on outdoor sim. Since we did not use surface reconstructions to generate dense depth map as in prior work, we are able to avoid surface reconstruction failure and shows more complete results. Here is an example of our pipeline runs in a VR headset. And here are more result video. Now, in this presentation, we present you a novel pipeline that can create 6 of content using a set of 360 images. We show how we reconstruct depth for 360 images, and we demonstrate our pipeline can be directly used in VR application. Our work is far from perfect and has really large room for improvement. Firstly, we're thinking of replacing some components of our pipeline with learning-based method. For instance, we might use NERF to do dense estimation. Although we mentioned that NERF currently has limitations on large-scale sims, we believe it can be solved in the near future. So NERF is still a really good next step to look into. Another future improvement we're thinking of is to make our pipeline work with dynamic sims. One limitation of our current pipeline is it only works with static sims. Any dynamic object shows in the sim will cause visual artifact because we did not address their movement. So it will be good to solve this issue, then our pipeline can also generate 6 stock video. Thank you for your attention.
Thank you very much. So let's move to the question Q&A time. So are there any questions from the floor?
Yeah, thanks for your presentation. So I had one question. So if I understand correctly, you take a set of 360-degree images and then use them to reconstruct at depth and for novel view synthesis. So do you have some insights on, like, say, how many of these spherical images you need to take, say, for outdoor scene and for indoor scene, and at what baseline distance you need to take them to, like, say, recover the depth reliably?
Do you hear our question? Okay.
Can you hear me?
Yes, please.
Okay, great. Thanks for the question. The number of images, it's not actually constrained. Like if you're using more images, you're able to reconstructing a large scene. So in our testing for for indoor scenes, we're using like less like around 10 images to 20 images. And for our outdoor scenes, we use like around 20 images as well. So, and then the baselines between the cameras, we're currently using a baseline that's around 40 centimeters apart each camera. That's not strictly the distance we're using because we simply extracting frames from the video, but that's roughly how it's the distance that we're using.
Okay, that answers my question. Thanks.
Thank you very much. So are there any other questions? Yeah, I have a question. In the demonstration video, I'm impressed the quality of the video. It's very clear. So I would like to confirm how the shooting viewpoint and the rendering viewpoint is different.
Sorry, I didn't quite capture the question.
As you said, the baseline is about 40 centimeter. So
Mm-hmm.
I think you capture the target scene is very densely located multi-viewpoint cameras.
Mm-hmm.
Okay? And you are generating the free viewpoint video.
Mm-hmm.
But I would like to know the distance between the shooting point and the generated viewpoint.
Yeah.
So how much the difference?
Oh.
Can you move the viewpoint drastically from the shooting point?
Yes. So like you can move away from the shooting point like quite far away, say like you can move about 50 meters apart away from the capturing point, and I mean 50 centimeters away from the shooting point, and it wouldn't break the scene too severely. But if you're trying to go further away, then the image-based rendering part doesn't work really well anymore because it was just too far away from the capturing point. So it basically becomes like you're viewing the 3D model itself.
Okay,
I see. So it will become not that clear. Yeah.
Okay, thank you very much. So are there any other questions from the floor? Okay. Okay, so thank you very much. So let's move to the final presentation of this session. In-person presentation, content-aware brightness solving and error mitigation in large-scale multi-projection mapping. This is a TVCG paper and given by Philippe Cruz, Marcus Hirschner, Mark Staminger, and Frank Bauer. So please start if you're ready.
Okay, hello everybody. My name is Philipp. I'm from the University of Erlangen-Nuremberg in Germany. Okay, thanks. So in projection mapping, you have multiple projectors illuminating a real-world object in order to change its look. So for example, in this image, this target object is actually white, and all the colors you see on its surface come from the 7 projectors in this scene. And usually that's combined then further with object tracking for dynamic setup. So in this case, in our case, we use these RGBD cameras and track the objects using the depth stream. So an example of this is this painting application we built. Oh, that's not my screen. So that's not my image. I'm sorry, guys. Let's start this again. Okay, so that were the RGBD cameras I talked about, and this is the example application which we built a while back, which allowed the users to interactively change the look of an object, and thanks to the tracking, you can move the object and the projection stays aligned with the real object. So a common problem in projection mapping with multiple projectors is achieving a uniform brightness. So in this example with 2 projectors, the overlap region is much brighter than the rest. We want something more like this, where the brightness is uniform over the whole surface. And therefore, we use a solver which adjusts the brightness of each projector pixel in real time. So additionally to the brightness solver, for a nice experience, we also need a high-quality mesh, then accurate object tracking, and a high-quality calibration of all the hardware components. And in practice, none of these factors are actually perfect, right? So then in practice, you always get some artifacts. And this is a general problem, but we note that these artifacts tend to show up more on certain areas of the surface. And therefore, we call these areas sensitive. And in the paper, we categorize multiple such sensitivities, but in this talk, I will focus only on 2. So in the image here, the projection that is supposed to hit the nose actually hits the cheek of the object. And that's due to calibration errors. And since this is mostly visible around silhouettes, we call this the silhouette sensitivity. So another problem is around high-frequency changes in the projected content. So if the calibration is erroneous, this leads then to ghosting artifacts, like shown here. And we call these content sensitivities because they happen around high-frequency content edges. So silhouette sensitivities are always a problem, but since ghosting can only happen with multiple projectors, content sensitivities are only present in setups with more than one projector. So, okay, so the contributions of our paper are then the vocabulary about these sensitivities, which we already talked about. And then in the following, we show I will show our novel brightness solver approach, which is built on a recent publication by Nomoto et al. But is extended to consider these sensitivity types. So the system supports large projector setups with upwards of 7 projectors without solving a complicated global optimization problem. And our source code is open, and we show a link at the end of this presentation. Okay, so the brightness solver assigns each projector pixel a weighting factor, which is then multiplied to the rendered color. And I will skip a lot of details here because you can read them up in the paper, but essentially the weight has 2 jobs. So first, it compensates for the attenuation due to physical factors. And this is, for example, the distance to the target object and the incident angle. And second, it balances the contributions of all projector pixels. And this is usually done according to a per pixel quality metric, again, based on the attenuation. So this solution is very simple and very fast to calculate. However, as I said before, the color that is finally sent to the projector is the multiplication or the product of the weight with the original rendered color. And this value is bounded, since values over 1 cannot be displayed by the projector. And therefore, the weighting factor is limited in range. So I give an example here for 2 projectors, each with an attenuation factor. And this results in one weight getting very small and the other one getting very large. And depending on the input color, this might then violate the inequality above. And if we clamp the resulting color, this might not achieve the target brightness, even though the second projector has the potential to contribute more brightness. So our solution then is an iterative weight assignment. So for each surface point, we collect all projectors which see this point. We then assign the weights, just like I showed before, but we clamp them so that they remain in the valid range. And then we evaluate the surface color for the current weighting factors by summing up the weighted and attenuated colors for each projector. So if everything worked, then I prime here should be the same as the input color I. However, if they are not equal, one or more of the projectors must have reached their maximum brightness, and then we just remove these from the list and distribute the remaining weight between all other projectors by repeating this step. And the superscript k here is the iterative process. So we terminate if the target color is reached, no projectors are left, or a maximum number of iterations is reached. And the nice part about this iterative solver is that it will later allow us to introduce constraints into this solver, which then consider these sensitivity types I talked before. Okay, so let's talk about these sensitivities. So here I show a schematic view of a projector illuminating a cube target object. And the actual position of the projector differs very slightly from the position determined by the calibration. So then this leads to content spilling over the silhouettes. So for example, the yellow projection intended for the upper cube then ends up on the background. So we propose to mitigate this problem by detecting edges in the render depth for each projector and then limit the contribution around these areas. So for single projector setups, this introduces a black border, like shown here. However, with multiple projectors, usually not all of them perceive a silhouette at the same points, so other projectors can then compensate for the missing brightness. So here we show the resulting mask for a setup with 2 projectors, and the intensity of pixels around silhouettes is limited. And we call this a hard mask because it imposes a hard upper limit on the projector's intensity for certain pixels. Okay, so for content sensitivities, we show here a schematic for a two-projector setup shining onto a flat surface. And at the point P, the content transitions rapidly from red to green, introducing a content edge. So in the bottom, we show a graph of the intensity weight for the two projectors, which does not consider the content. Note that at point P, both projectors account for non-zero amounts of projected intensity, and this might lead to ghosting in the presence of calibration errors. So if only one projector was responsible for the illumination at P, ghosting would be impossible. So similar as before, we propose to detect content edges in the rendered images, and in the example here, we then boost the intensity of projector 1 while lowering projector 2's around the content edge. And since now only one projector projects this edge, ghosting is impossible, and we essentially shift the transition to low frequency areas in the image. So the difference to the silhouette sensitivities is this, that all projectors perceive the same content edge, so a hard limit does not work. So instead, we would like the best hitting projector, so that's projector 1 in this case, because it has the best incident angle, to contribute as much intensity as possible, while other projectors fill the remaining intensity if necessary. So in addition to the hard mask, we therefore compute per pixel whether each projector is the best hitting one, so the one with the best incident angle. And then in addition, we detect edges in the rendered color image. And if a projector is not the best, we provide a hint to the solver to reduce this projector's weight around edges. So this mask is called soft because it is not enforced. It merely acts as a hint to the solver, but if the required intensity is not reached, even projectors with small soft mask values are required to increase their brightness. Okay, in terms of implementation, the hard mask caps the maximum intensity assigned by the solver, and the soft mask modifies the initial weight assigned to a pixel. And this increases the relative weight of the best hitting projector, and then if the best hitting projector cannot account for the total required intensity, others will automatically compensate. So the nice part about our iterative solver from before is that this is all we need to account for the constraints. So if one projector intensity is capped, the resulting brightness will not add up to the target intensity, and then the solver will simply assign more weight to other projectors in the next iterations. And we color code this iteration count here, and as you can see, more iterations are usually required around silhouettes for one of the projectors. And this is exactly because, due to the intensity limit, the solver must assign the remaining weight in later iterations. Okay, let's evaluate the effectiveness of our solution. So on the left here, we show a projection completely without a solver in a 7-projector setup. And this is a typical calibration quality we achieve with our consumer-grade hardware. And you can clearly see the artifacts and the ghosting. So here I show the projection quality with all corrections applied. And I hope you can see that the image is much nicer and much more uniform, and the ghosting is greatly reduced. Okay, in this example from earlier, I showed the projection spilling over the nose to the cheek, and the hard mask helps here and mitigates this artifact. Lastly, the soft mask reduces the ghosting quite a bit, and there are still some artifacts left in this red rectangle region, and this is because this is close to the border of one of the projector images, and there the solver has no other choice than to transition between the projectors. Okay, here I show an internal view into our mask for a setup with 2 target objects and dynamic content. And all masks are recomputed each frame, and that allows our system to handle dynamic content with shifting content edges. Okay, in terms of performance, this table evaluates our system. And for a detailed evaluation, please refer to our paper. But the important value here is this circled one. which shows that even in a 7-projector setups, our system fits well inside the real-time budget on a consumer-grade GPU. Okay, so again, we publish our source code openly under this link, and it includes the brightness solver I talked about, and it also has solutions for calibration and object tracking and systems with more than one computer, which you need if you have many projectors. Okay, that's it for me. Thanks for listening.
Thank you very much. So are there any question or comment from the floor? I have a question. Right now, you show the demonstration using 7 projectors. Mm-hmm. In that case, how do you give the priority to each projector, or is it given by automatically? Okay, so I initially assign the weights based on their incident angle and their distance to the target, right? And then only if certain projectors are capped from the hard or soft mask, then this requires other projectors to compensate. So that's the weight assignment or the intensity assignment. So the initial priority given by the roughly shape of the target object? Not necessarily by the shape, but more on like the incident angle of each projector ray, because in order to get the highest quality or the sharpest projection, you want to prioritize those projectors which shine like perpendicular or like head on to the surface, because then the pixel footprint is the smallest. And that's why we usually prioritize these projectors. Okay, I see, thank you. So are there any other questions from the audience? Please give him the microphone. There's a microphone. Please raise your hand once again.
All right, thank you. Jeroen Steeds from Hasselt University here. I was just wondering, I don't know if this was mentioned in the talk as well, but is there actually like limitations with some objects that you can also support, or like multi-object support as well that you can protect upon?
Yeah, the method is actually agnostic to the actual target objects, so it all works on the rendered images from the system. So that's the only part that actually uses the meshes or something. So and in the video, you actually like saw multiple target objects, right? Mm-hmm. So maybe a limitation of the hard mask, for example, is as you can see here on the nose. Oh, can you show my screen again, please? So as I said, the hard mask might introduce like black borders to silhouettes. So that's one limitation, and you can actually see here on the right that the nose is slightly darker than on the left, and that's because of the hard mask, and the other projector cannot actually like compensate fully for this for the thing. But it's in our experience still better than like projecting over the edge.
Yeah, indeed. Thank you very much. Very interesting.
Thank you very much. So are there any questions? Okay. So thank you very much.
Thanks.
So this is all this session. So we would like to conclude this session to thank everyone who attended this session. Thank you very much. And please also enjoy poster before leaving to the social events. Thank you very much.